Welcome to APEC. It's July 8th, and I'm your moderator, Tim Ventura. First, I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. Today, Dr. Chance Glenn will be discussing warp bubble drive research. Dr. William Rieken will describe a new hybrid rotational detonation engine, and Jarod Yates will explain the TR-3 Black Manta. We'll also be hearing community news headlines from our media partners and finishing off the event with open discussion and potentially ad hoc presentations. So after that, our lab partners will provide updates on their latest research and experimental headlines. Our media partners will provide news headlines on their top stories. And we are just going to go through everything and give you the absolute best. So some quick updates here. We are doing webinars through StreamYard every month. As you know, the open discussion is through Zoom 2 weeks after each webinar. This lets us keep the presentations free of distractions, gives our open discussions the flexibility to focus on a greater variety of topics. So today's event is on StreamYard. It's broadcasting through the Alt Propulsion YouTube channel as well as the Alien Scientist channel. If you haven't subscribed, please subscribe. You can ask questions using the live chat feature on the right-hand side of the page, and we'll ask them to our presenters depending on time constraints. You can also always view conference replays, details, and speaker info on our website at altpropulsion.com. So without any further ado, I want to introduce our first speaker. I am honored to provide you with Dr. Chance Glenn, the Provost Vice President of Academic Affairs at the University of Houston, Victoria, who has been working on experimental spacetime distortion and warp bubble research. Okay,
well,
Chance,
all right,
welcome, sir.
Welcome. All right, thank you, Tim. How you doing? How's everybody out there?
Doing well. And so let me I'm going to bring in your slideshow as well. Okay, there we go.
Yeah.
And you should be able to thumb right through this. And what I will do is while you're presenting, I'll take myself out of the stream. And so, yeah, whenever you're ready to get started, sir.
All right. Well, I am here at the lab here at the University of Houston, Victoria, where I do conduct some of my research. And I'm also representing the Morningbird Foundation and the research that we undertake there, which supports our STEM education and research initiatives. And that is the primary function and mission of the Morningbird Foundation. And you can learn more about that on the website, morningbirdfoundation.org. But what I want to discuss today is really working towards an experimental verification of space-time distortion, of being able to do it ourselves in a laboratory under controlled settings in order to begin to build a pathway towards warping space-time and perhaps even superluminal travel, propulsion, which is kind of, I guess, the holy grail. And this is how we will lay out the presentation. I'll give you the rationale, which you probably are all very much familiar with. Then the background, the approach I'm taking, modeling and simulation of that approach, the experimental approach, and then some of the implications of what it would mean should we be successful. And finally, just some of the collaboration that I've been involved with so far, and also just letting you know that I'm looking for further collaboration. So if some things that I talk about, say here, spark some ideas and perhaps potential collaboration, I would be more than happy to hear from you and work with you, and I'll let you know how to connect with me once we're all done. Okay, so as I said, many of you know most of this. Our current space travel capabilities has its limitations. Right now, probably the fastest known man-made object is that NASA solar probe, clocking at about 531,000 kilometers per hour. And there are different missions that we're trying to undertake that just within the solar system that are just daunting to think about when you really start looking at the potential distances involved and the speeds required, because one of the issues with the speed obviously is that you have to accelerate up to those speeds, and there's a limitation to the amount of acceleration a human body. So if we're talking about human travel limitations, and in addition, kind of our cosmic speed limit at the and I know some of that is a little bit controversial, but the speed of light kind of being the fastest speed that physical matter can move within real space-time. Now, just giving you an idea, you've seen these before where you kind of move outward and you see just how far we're talking about. So you had 10 billion kilometers looking at our major part of our solar system. As you go out to finally 1 light year, we're just outside of our solar system to the Oort cloud. As you get further, 10 light years, this is where you see our nearest stars, our neighboring stars. You see the Alpha Centauri, Sirius, those stars that, if we were going to try to travel to other star systems, these would be candidates. And you can see just how far just 10 light years would be. If you could travel at the speed of light, it would take you 10 years to get there. Under our current propulsion, it's unthinkable. The Milky Way galaxy where we live, a little bit more than 100,000 light years across. So being able to move about our galaxy, we would have to be able to travel at speeds in excess of the speed of light. So in any case, and finally, the universe itself, at least well known, there's billions of light years that you would need to traverse such distances if you want to travel about the universe. Now, this is where the background of all of this comes. And Alcubierre developed this metric, and this is a particular solution or particular metric that he put forward that suppose that if you could bend space-time, and the graphic you see at the top left, it's been kind of popularized because it looks nice, but it gives you kind of an idea. But when you see this part going down, that actually means that space-time is being compressed, and in the back of the vessel, the space-time is being stretched. If you were to do that, and that's what this metric supposes, then you would be able to move a vessel forward. And it even suggests that with enough energy, you could even travel faster than light. Another good analogy to think of is that if you were sitting in your car and you want to travel down a road, normally you press the accelerator, the car starts moving. But instead, what if the whole road and everything around it was moving and the car was standing still? You would get to your destination, but you would not feel the inertial effects because everything else is moving around you. This is kind of the idea. All right, so and that's what I have in this slide, just to give you that picture. Now, here is the particular shaping function. If I go back to the metric, this f of r is the shaping function that Alcubierre suggested. This is the mathematical equation here, and this is what it would look like visually as you go out in radius. And the York time measure that falls out of it is directly proportional to the derivative of the shaping function with respect to the radius. And that's where you see that this, again, this kind of negative means you're compressing space-time, and this positive means that you are stretching it. The vessel is here within this flat or relatively flat space-time that the vessel would reside. So if you could move much faster than light, I'll just give you some examples here of what would happen if you would want to just travel around the world by a method that you were at 0.5 C. You could get around the world in less than a second. And here's other things. See the nearest star, if you could move at 10 times the speed of light, you could get there in about 5 months, which is a reasonable time for a human space travel. But it's one thing to say all of this, it's another thing to try to actually do it. And this is a little bit better depiction of what happens. First of all, you see that, you know, space-time is compressed here, is stretched behind. Inside is probably the most significant part of the vessel. But the thing I wanted to also make it clear is that whatever you're doing to stretch and compress space-time is contained within your bubble, but your material, some have proposed this, some of this should utilize your exotic material that some have suggested, but it all has to be contained within that, not, you know, some of the other visual that we showed kind of implied that the space-time, that the vessels, those round appendages around the vessels are what causes the space-time to distort, but it's outside of that, but it should be inside of your material and everything. And I'll be a little more descriptive in a second. Okay, but here's the problem. Here's the problem. In order to do this, there was a energy density requirement calculated by Alcubierre. And in that solution, not only was the energy density requirement enormous, but also it was negative. And while some researchers are mentioned here worked to reduce the magnitude of the energy density requirement, the polarity of it, if you will, was still negative. And that was an issue because no one really knows what negative energy is. I know there's been some speculation around Casimir effect, for example. Some have suggested some sort of exotic material that would lead you to there. Antimatter, all these different approaches to try to overcome this. So this is the drops out of Einstein's equations, and this is the energy density expression that comes from the Alcubierre metric. And as you can see, there's a big giant negative sign right here. All of these terms are squared, so you know it doesn't seem that there's a way to turn that negative sign positive till I looked at this. Now, my background's in electrical engineering, and I you know played around with complex numbers and all that, and know that if you have an imaginary number and you square it, then it becomes negative. And then if you multiply the negative with the negative, now you can turn this equation positive. So what I was looking at was what would it take to do that, and with the shaping function, because that's something that you could have control over. These other things you don't have as much control over. So the shaping function, if we had a value of it that has a imaginary component that is greater than the real component. Then when you square it, it becomes negative, and then this energy density becomes positive. So that's the mathematical basis of what I was coming after this with, and this kind of just walks through that. And in a simulation of that, you see now the energy density, which before was negative and pointing downward, now is positive for the right values. Now, it's one thing, again, is mathematical, but I began to sort of say, is there anything practical that could be derived out of this? And so I began looking at materials, because again, as an RF engineer, have familiarity with dielectrics and their interactions with RF as an electromagnetic wave passes through a dielectric material, what happens. And so I began looking in that space, and again, to essentially try to find a dielectric material that has a property of a complex, having a complex dielectric constant, relative dielectric constant. And lo and behold, I was able to find one. It's something called ethylene glycol. And you're probably very familiar with it, because it is essentially a coolant or an antifreeze, but at the right temperatures and at the right frequencies, it has a relative dielectric constant where the imaginary part is greater than the real part. Now, RF engineers don't like this, because if you're trying to send a signal through a material, you don't want it to be absorbed. And this is what's called a lossy material. But if you think about it in another way, it's storing up energy. And what is it doing with that energy, and how's it being dissipated? And so then I began looking at the molecules themselves. Now, it looks like I'm not able to actually play this video, but in the other slide there's a link to a video that kind of shows what happens to this ethylene glycol molecule as the energy is applied to it. And what you'll see is that there are variations or twists and turns, instead of just in most lattices where the energy is passed through, then the phonons cause energy to pass through, and it just vibrates back and forth. In this, there are twists and turns that happen, and I think that is where the complex dielectric constant comes from, because these numbers, for example, are developed from the Debye model, and it is modeled as having that particular value, and you'll get this rotational type of movement, as well as that back and forward. Now, again, I'm just going to speculate, and this is speculate and even not even a hypothesis, I would say. But if the molecules themselves are connected to space-time, then perhaps the twisting and turning and tugging on space-time itself, it could allow some distortion to happen in a material like that, with the right frequency and with the right temperature. And that's the speculation. This is, the permittivity of a dielectric material. As you can see, the relative permittivity being like this. And it just kind of showing the same thing I showed before, that if you square that, now you have a value that the real part will be less than 0, and therefore multiply and make the overall energy density if you use it. Now, this is what I was getting at. So you have an energy that is, well, in this case, an electric field that enters into a material, and with real dielectric constant, you'll have the electric field exit, and it may be smaller in magnitude, but it does, exit without much distortion. In this case, and again, with it being lossy, you do have this rotational action of the molecules that happens, and the new electric field is much less than that which was initially put into the material, and therefore that's where you get the lossy behavior. Now that's why RF engineers and others just kind of, and those who work with light as well, just kind of avoid this type of material, because you lose the energy that you put in. Now, just to kind of take it forward, I mentioned that the numbers that you saw on the table were developed from a Dubai model. So I wanted to do some measurements. And one of the things I did, I made a little slight modification to the material by adding a gelatin, because the ethylene glycol is a liquid, it's a clear liquid. And I made a gelatin just so that it would fit within the chamber I was developing a little bit without leaking out and all that. But I did change the properties. Excuse me, I'm trying to get my lighting back. Give me 1 second. Sorry about that. I'm in a lab that has time lighting and I can't do anything about it at the moment. Okay, but it has this we actually sent this down to the University of South Florida, had them do dielectric measurements. Now, what you'll see is that essentially the behavior that we were looking for got pushed out to beyond 4.5 gigahertz. So right around almost 5 gigahertz, you start to see the imaginary part, the real part being greater than the imaginary part being greater than the real part. That's the blue line is the imaginary part, and the red line is the real part. So that behavior happens out here. I'm having them measure the pure liquid. I don't have that data yet, but I expect it to be back here. But I wanted to see whether this gelatin would work the same way. But I do see, you see the kind of the modifications to the values. All right, but so what I'm looking to do is to create a cylindrical resonant cavity filled with this material, and then excited with an electric field in the TM010 mode at around 2.5 gigahertz. And so we would have this type of distribution of the field, which essentially is almost like a half cosine. But in any case, this is the distribution of the field. So you'll see that it has a distribution that has a differential across with respect to the radius. So therefore, you can get some change, and that's what you need, is some change. dr has to not be zero in order for there to be some action that or hopefully we'll see. So this is what it would look like instead of this top hat hyperbolic tangent type of shaping function that Alcubierre put forward. Now, so in this case, this is what the shaping function would be from the center outward, and then if you do analysis of the energy density in the York time, you would have to kind of look at York time by turning this graph in probably 190 degrees. But as you can see here, the energy density that you're expecting is similar to what you saw with in Alcubierre's work. So we're just trying to again get some change there, but the important part of it is that it is positive. Those are positive values for the energy density. The York time model kind of looks like this for it. It doesn't have that flat center. Now, look, this is not something that we're trying to put a ship in and start propelling things. What I'm trying to do is just show that we can experimentally distort space-time under the right conditions, and then it gives us something to work with. And I just want to detect that space-time has been distorted at some level within the chamber. That's my goal. And having shown that, then you can start to take it to other levels of determining use cases and things of that nature. Now, so within the chamber, in order to do some more analysis here, you want to calculate the energy density within the chamber due to the RF, and then equate that to the energy density in order to, given by the Einstein's equations, in order to try to come up with an expression for what distortions we would see versus how much input power we would apply. That's what this is. And so the calculation to determine the power density inside, then by equating it to the energy density, we're calculating the energy density inside due to the input power, equating it to the energy density due to Alcubierre's work. And this is what you get. And this is essentially an expression of the maximum input power versus how much distortion, that's what delta X is, that you would see. Now, as you might expect, the power levels are very high if you want to get any reasonable distortion. But what I want to find out is what a measurable distortion. And in a few minutes, I'll make the case that nanometers are indeed measurable. And if I can get distortion on the order of just nanometers, I would only need, as you can see here, roughly 10 watts would give you just over, let's just say that's about 30 nanometers of displacement and so on. And you could get a little bit less back here. And as you can go up in power, you could get a little bit more. Now, of course, given the physical experiment that we're looking at, there'd be some limitations on just how much power the chamber itself could stand. But again, I want to be able to detect nanometers of movement, and then we could make our experiments more and more sophisticated. So I have this, some of you probably familiar with COMSOL. It's a pretty comprehensive simulation package, and I'm using that to model this chamber, which I'll show you what it looks like in a second, and to measure what happens with the fields within the chamber. You could also measure things like temperature and pressure as well, and model and simulate that. So I'm working on that, which, as you know, it allows you to do this pretty detailed analysis if you're pretty familiar with it. This is what one looks like. I've actually fabricated. Matter of fact, I'll just go and pick this up. This is the chamber and the fixture. Now, what you see is a hole through the center, and I'll describe what that is in a minute. But what this basically does is RF is pumped into it through here. This is approximately the right size given the material inside and the frequency of interest. and then it's set up to work within an interferometer, which this is the experimental approach that I want to describe to you. So if many of you are familiar with the interferometer, you probably know that gravitational waves are being detected using a large interferometer, the LIGO experiment. So think of it like that. But what happens is that if space-time is distorted in any way, then its path is disrupted. And if you can disrupt its path, then you can detect it with an interferometer. So I have a 532 nanometer laser sitting right over there. And this laser goes through, it's split at the beam splitter, bounces off the mirror here, comes back, goes through the hole in the chamber. So I have to, really set this and establish this in the right position, which I took it out. So now I'm going to have to go back and do it again. But such that the beam goes through, bounces off the mirror, comes back through that hole, and comes to the splitter, combines here, and that's where you'll see the interference fringes. Now, I have a 2.5 gigahertz source, amplifier, and for now, currently, I'm trying to get my amplifier to work to give me about 10 watts. But as I've been talking to some here, I might be able to get something a little bit better. Here's a key point, and I want to focus on this. This pulse generator, I'm going to pulse the power. Reason I want to do that is, number one, I want to be able to make sure that any other extraneous movement, noise, and other things are not impacting that. That's not what we're reading. So if I'm pulsing this power at the right levels, at the right pulse rate, and duty cycles and all that, I'll be able to detect whether it is my actions or the actions of the signal the RF that is creating the distortions that are picked up at the screen here. I will be able to determine that versus some other action that might be happening, because essentially you can stomp your feet or bang the table or whatever, you'll see movement on the interferometer. So it's very, very sensitive measurement. So I want to make sure you're eliminating other type of interference. But this is the experiment diagram of what we're going to be doing. And it gives you these type of fringes. I have some better pictures, but this is essentially what you're looking at. The 532 nanometer laser is green, but this is the setup, and this is where you see it. And I showed you the picture earlier where the chamber actually was sitting in between here, and tuned just so that the beam goes back and forward through it. Now, so just a simple way of measuring it was basically shining a camera at the interference fringes that you see on the screen, and this picture up here is what it looks like. And I just did a test of just moving the mirror around here, and as I measured a frame to frame error at 30 frames per second, you see that if there's changes going on, then you would actually see this picked up. So my hope is that as I'm pulsing the chamber with the RF at the right rate, you'll see distortions happen at that same pulse rate and on the order of what we're looking at. And if it does happen, then I'll know experimentally that we caused it. So we intend to show this process by which we can experimentally distort space-time in a controlled environment in a repeatable fashion, and that's going to be key. So once we're know we can do this. You should be able to replicate it in your labs. I want to show that a combination of materials and the geometry and the input power has a potential to do this in the desired fashion. Now, a point I'd kind of skated over, and I want to come back and just make sure it's clear that we're also looking at metamaterials as a way to do this, and being able to design metamaterials that have these kind of complex dielectric characteristics, and then do that, because it could be easier to work with in some sort of liquid or gel or some other material. So that's the approach that I'm trying to take in order to do that. I'm supposing that this kind of tugging of is happening at the molecular level, this tugging on space-time. That's the action that is happening, and that's what the energy is doing, is tugging on these molecules, which is therefore tugging on space-time, which is causing the distortions. And that's why the complex material does it, because it has this rotational motion versus just straightforward phonons within the lattice. And again, kind of backing up to the equations that Alcubierre put forward, that's why I believe that the complex number inside that squared term is what makes the energy density requirement positive. It's using the energy to do the things that I'm talking about. So that's again my hypothesis, and we're going to probably be arguing over that for years to come. Now, controlled space-time distortions not only have implications for propulsion, but also containing reaction, manipulating energy, shaping fields, a lot of different things. And I've been working with some people who are looking at it for a particular purpose, and we want to see if this method is a way to do it. And we're looking at some other methods also. And then we'll learn more about energy and material requirements that we need to carry out space-time distortion and manipulation by taking this approach. So could we scale this up to something that would allow a ship to be propelled through the far reaches of space at faster than light speeds? Perhaps. But we've got to show that we can do it first at the smallest of level. Now, we know that all matter and energy manipulate space-time. Everything has a gravitational field, in virtue of E equals mc squared. It goes back and forth. It's energy matter duality. We just have to figure out how to utilize it in a repeatable fashion, in a way that we can begin to exploit it. And that's just the approach I'm trying to take. This is just my background. I mentioned the Morning Bird Foundation. That's what I do there. This is the connections that I've been building over the years through some of the universities I've worked with, as well as these organizations that I work with. And this is just some of the imagery that kind of shows that I've been doing that. There's the NASA meeting. This is at NASA headquarters in the Marshall Space Flight Center headquarters in Huntsville. This is at Johns Hopkins. These are some of the deans of engineering from the different HBCUs and MSIs around the country. This is Dr. Sonny White and I at his place, Limitless Space. This is Greg Hodgkin at ZC Institute. I said is working together with a team of people looking at some very interesting things, and I'll let him talk more about it when he gets the chance, if he so chooses. This is work at SpaceX that I do and continuously do. So, and just to summarize, this is just to establish a framework for controlled experimental distortion of space-time. That's what I'm trying to accomplish. I want to show definitively that a complex dielectric material having the right values is what can make this happen, and where perhaps a non-exotic material, unless you want to call this an exotic material, but this is what allows you to be able to do it. Then we've derived this experiment using this Michelson interferometer, which will provide the resolution necessary to detect a small distortion. And we intend to work with others, and I'm looking forward to doing that, working with others to improve all of these different aspects in order to try to make this happen. And I'm looking forward to that. This is just some of the references, and these slides they can be made available to however you want to do that. And so let me just finally say a couple of things. One is that as I said, I'm looking forward to working with people. I'm looking forward to hearing your thoughts on our approach. If there are others doing something similar or in a different way, I'd love to hear that, because I think that if we're going to do this, whether you're interested in traveling at superluminal speeds or anti-gravity or whatever, other utilizing energy and things like that, if we're going to do all that, we have to collaborate, but in ways without fear of this is my idea, this is your idea, and all that stuff that happens. But I'm looking forward to working with people. The other thing is that one technical point I want to make clear again with this chamber is I'm trying to get just movement of distortion within the chamber. And what I think what happens with the mathematics is that people have gotten used to just plugging a velocity into that expression, say, all right, if I want to go this fast, I plug the velocity in, that tells me how much energy I need. But it is the shape of the space-time distortions that allow for movement, and the movement in relation to time is what gives you the velocity. So if you don't compress in one side and stretch on the other side, and you do something else, then you won't move. So for example, if you compressed on both sides, you won't move, but you'll still be distorting space-time. And you may want to do that for some reason. So you would still have to put in a certain amount of energy in there to do that, but you won't be zipping off, into the cosmos. So I just want to make sure that it's understood that the shaping function and what you're actually doing to space-time is what determines the velocities that you propel or don't propel, or whatever it is you're actually trying to do. Because you may be able to formulate small wormholes or rip space-time if you put too much energy in, or some other thing that you might want to do. Thinking about the shape of the shaping function, what you're doing to space-time, that's how we should be engineering the uses that we're starting to speculate about. So I just wanted to make that point at the end. But with that, looks like I'm ending up a little bit early, but that's all I have to say on it. And I don't know if you're having questions or how you might be going about it, but I'll end it right here, Tim.
What wonderful. Okay, well, Chance, thank you so much. Thank you so much. So let me do this. I'm going to take down your slide share really quick. Okay. And you know what? I want to put everybody into the stream here. Let's give you a big applause. But let me, I wish there was a button to add everyone all at once. Let me see. I think I've got everybody there. Let's give Dr. Chance Glenn an enormous hand. That was a
Thank you.
wonderful, wonderful presentation. Chance, your work is absolutely amazing, and your reputation absolutely precedes you. I should say that. People have been saying you got to get Chance on to present. So
Okay.
thank you, thank you.
Appreciate that. Thank you.
So yeah, we've got about 10 minutes left, and we've got, let me see, we've got the crew on. Let's do some Q&A, and then we can also take questions from chat as well. And I think Mark is working on that. You can see Mark is actually doing testing as we speak.
Okay. Yeah. I was talking to Mark a little earlier, and they trying to see if we can get some equipment from him, because that would help.
Oh yeah, it's right here. Actually, I pulled it out. We had a spare amplifier sitting around, and you mentioned you needed 2.5 gigahertz. This one goes from 1.95 up to 3.8 gigahertz.
Oh, that's perfect.
Puts out a couple hundred watts.
Mm.
And get this, it's from Space Microwave Laboratories.
Oh, okay.
Pulse microwave amplifier. The company is defunct. I think it came from Sandia or Los Alamos.
Yeah, I'm familiar with them. I mean, back in my day, I worked with the Army Research Lab, and I was in RF, and we actually worked in high power microwaves. I'm used to working with gigawatts of power in anechoic chambers and stuff, trying to blow out front ends of communications and stuff like that. That's what we were doing back in the day. But yeah, so I know that company a little bit, and I would definitely love to have that. So as I said, I mean, if you can figure out how to ship it, I'll pay to have it shipped, but definitely need it because I don't have enough in this lab at the moment.
Okay, we'll definitely get it down to you. So,
all right.
Do we have any questions from the group over here before we start moving over to the chat? Everyone in the live stream here, you can unmute yourself if you got any questions for Chance.
I had a question from the audience from Jack Sarfati. He said he doesn't understand how you use this complex dielectric to get the 1 nanometer displacement that you predict. Do you get into
yeah, well, what my supposition is that by pulsing in RF into the chamber that has this material in it, the field distribution essentially gives you your shaping function, which, since it's not flat, it has some differential, then there can be some movement. And my hope is that the movement of space-time within the chamber will pass through where the light beam is going through, and then my hope is that then we detect it with the interferometer. So I'm just trying to create a distortion within the chamber with the pumped RF, setting up the fields the way that are described, and with that, again, hopefully distorting space-time that then would be detected.
Okay, sorry about that. And I'm just I'm working with Will a little bit in the background. He's having some problems. He may not be able to play some of the videos for his presentation in a moment, but we'll get to that when we get to that. So,
okay.
Chance,
Yes.
back to the slide where you had the different TM modes. I saw you were simulating it for a range of different frequencies. What mode are you planning on using? What's the shape of the chamber going to be?
TM010. TM010.
TM010.
Yeah.
Okay, but the chamber right next to me over here, this way, is it's a TM110 with feed from the side, and that's great for I'll get to it later. I'll explain it to you why. So it'll be a cylindrical shape then, right?
Yeah, I mean, that's what that's essentially what. Where's my camera? Oh, that's essentially what this is.
Well, it's got to be bigger than that. For 2.5 gigahertz, you're going to want something like probably.
No, but that's because the material inside the dielectric constant is high, so the wavelength is. So I'm calculated it down to about 17 millimeters. Is the wavelength? Is the diameter required after, because the material's real part of the dielectric constant is 12.21.
Well, at 2.5 gigahertz, your wavelength is about 100 millimeters. So
But
one
inside,
refers
but are you
to
calculating
radius.
it with the material, with the dielectric material? Because it's V over F, and V is epsilon C. So epsilon is epsilon R times epsilon 0, and epsilon R is 12. So it's making it smaller. So
Okay,
um,
well, have some extra pipe on hand because it might be.
I know, and I'm gonna have to.
The good thing about this amplifier, though, is it has a wide range. So if you're off, you can just turn your dial a little bit.
Yeah, no, that's right. And the thing that it is a concern is with the size is that the energy density inside is determined by the volume, and and it's over the volume, so divided by the volume. So as the power goes up, I could blow this thing open before I actually see something happen. But my hope is that again, since I'm looking to detect nanometers in distortion, my power level only needs to be about somewhere between 1 and 10 watts.
This can pump out several hundred. So
Oh yeah, I know. Yeah, and if I can create a situation that allows me to put that much into that contained space, then that would be even better. But now you got temperature issues and pressure issues that you'll be creating as a result.
and that'll attributes to your noise floor.
Yeah.
If you're going to be looking at it with a laser interferometer, heat rising is not very good for an accurate measurement.
Right. And the heat rising is not good to keep the property of the material where I want it to be. So it's a delicate thing to try to keep it and balance it where I can actually see something happen.
And know that it's real. Yeah.
And know that it's real too. And that's right. But I'm sorry, go ahead.
Oh, so Michael Boyd, actually, and I should apologize for jumping in. Michael Boyd had asked, in fact, I'll put this up there. He was wondering, are you assuming that the speed of gravity is the speed of light? I'll put the comment up there.
I'm not. I don't have a need for that. I'm just hoping to see a change in the gradient. The gravity gradient. If it's somehow because there's a non-flat energy distribution within the chamber, then you see some movement of space-time within, and therefore detect it. That's just what I'm not trying to say I'm making some field that's going to cause us to propel a ship anywhere. I just want to see distortion that we caused. And if we can do that, then all of us start putting our heads together and minds together to start coming up with different ways to do it.
Yeah.
The presenter from last time, from a month ago, Dr. David Perez, actually achieved that as well. He's using much lower frequencies, but I believe with 2.5 gigahertz that you plan on playing with, you probably get better results at those higher frequencies, smaller containers, so the energy densities can get higher. Another thing to factor in is your Q factor, because every time the wave builds on itself, it's like adding another layer of that power. So if you get a Q factor of 1,000 instead of 200 watts, now you're at 200,000 watts equivalent.
Oh yeah. Well, it's not going to be that because of the losses in the material itself, because of it is a lossy material, it's going to dissipate that energy. So it's not going to build up like that. I think my biggest culprit is going to be heat. What happens, and if heat distorts everything I'm trying to measure, I might have to cool it as I push up. And again, I probably have to redesign the chamber. It's just the first attempt, and I'm playing around again with tenths of a watt, but I'm probably not going to see much with that. But that's the way I'm going with it. I have a colleague I've been talking to. He's looking at it from a magnetic standpoint, which would also be very interesting. I am familiar with what Dr. Perez is doing. I know something about fractals and fractal dynamics because I've done some research in chaos and chaos theory back in my other life as well. I don't understand his, fractal antenna approach and how that translates into space-time distortion. But take him at his word, at what he's
Just
measured
look at
in
the
the lab.
experiment.
Yeah, that's what I'm referring. I've seen that. So
yeah, look at the experiment and the theory. Put it aside, because just because he got an experiment right doesn't mean he has all the theory correct. Also, that's what I've seen with these kind of stuff.
You know, one of the things that jumps out at me, I love the fact that you were in a lab doing work, right? It's the same thing. I've been telling Mark this for like the last 2 weeks. I love the fact that you're in a lab doing work. That's amazing,
yes,
right?
and kudos for that. As soon as Chance started posting on Twitter components for his laser interferometer, I started commenting right away. I'm like, oh God, we got somebody else here who's playing with it.
Yeah. I mean, that's what I like doing. I mean, I'm an experimentalist, I think, at heart. I can go fairly deep with math, but only so far. I like to do stuff. I see a question popped up.
Yeah, well, and it bridges the gap, right? I mean, there's a lot of really great theoretical work being done, but ultimately somebody's got to put the pieces together to make it work. Somebody has to do the experiments, and the fact that you're doing those experiments is just brilliant. It's absolutely wonderful.
Thank you. I'm not familiar with reverse flyback voltage, so I haven't done any experiments like that. I see. But and this is really neat. I'm just
these are some of the benefits of StreamYard. Mark got me into this, and it has a lot of really nice advantages to it.
So this is actually a great question, and if you I can answer this too. But
please do. Yeah.
Oh, okay. So electromagnetic energy, or light, or RF, it travels through space. So the medium of its medium of travel is space-time. So it's doing something to space-time. In the near field, next to an antenna, we're actually building little warp fields all of the time, but they're equal and opposite. So what Chance is trying to do, and what David Perez has done already, and is trying to make these coherent waves where you're building on top of a wave that's already there. So instead of equal and opposite, it's the same each time, building. And eventually you create these depressions, and you can stretch space-time in certain places and create local distortions that you can, either ride on or pull things with, lift the cow up into the spacecraft, or, whatever you're trying to do. You can manipulate things at a distance by just manipulating the electromagnetic properties of space-time using coherent RF. It's very important. The tuning is the most important part, because if with a frequency that moves at the speed of light, you have to have it tuned perfectly or it won't work. And I've seen a video recently, I think it was on Instagram or something like that, of a laboratory related to the Navy where they can simulate waves, and they got it in perfect resonance with the size of the chamber. And when they're resonating like that, the peaks and the nodes do not move. They stay in the same place, and they build up on themselves until the system maxes out based on its cue. This is the exact same thing that we're doing, just with RF. And when you do it with RF, cool thing is now you have a hooking spot to latch onto and move your spacecraft around.
Okay. Well, guys, on that note, we are at the top of the hour, and we have Dr. Will Rieken coming up next, and he actually has a couple of folks that he's bringing with him. So if it's okay, again, everybody here, let's give Dr. Chance Glenn another applause.
Thank you.
Chance, thank you so much. And I meant every word that I said. I love the fact that you were doing experimental work. You have both theory and experiment, and just reaching out and collaborating with others in the community. It's amazing. It moves all of this forward.
And I'll be happy to communicate and connect with people. My email's chanceandglenn@morningbirdfoundation.org. And I appreciate you having me, and I'm going to hang around as long as I can for everybody else's stuff.
Wonderful. Thank you so much. Okay, so what I'm going to do now is I'm going to shuffle around. Let me see. I'll remove Chance and Mark and Jeremy. Okay, so I'm going to bring Will in. And so let me introduce Dr. Will Rieken, the man who needs no introduction. And then let me see, Raviv Yatam and Chris as well. Okay, and so you had a presentation, Will, and you have two colleagues with you. So do you want to start the presentation? How should we do this? I can put up your PowerPoint if you like. Oops, your sound is turned off, sir.
Sorry.
There we go. Okay, no,
Okay.
you're fine.
So I'll start it, then I'll pass it off to Christopher. He'll pass it off to Raviv, and then
Okay,
Raviv
well,
will pass it back to me.
I'll leave all of you gentlemen on the screen then, and I will hide myself. And then when we get to the videos, I may owe you a tremendous apology. I'm still learning some of the in and outs of StreamYard myself. But hopefully we'll be able to make that work. And again, thank you so much. Again, you guys are actually building things, doing experimental work, and it is brilliant. So this is the Hybrid Rotational Detonation Engine, right?
Yes, that's right.
Okay.
Yeah.
Well,
So, okay, go ahead. Oh, okay. So I'm introducing our work for the multi-mode RDE, which is a rotational detonation engine. So this technology is rather new and is disruptive, but is for affordable, high Mach, long range transportation and recreation and other uses. A rotating detonation engine, RDE, is a more compact and efficient method of creating thrust for various transportation systems. These are mechanically simple engines with no moving parts, which makes them less complex than gas turbines, also makes them lower cost and simpler to manufacture. RDEs RDEs burn fuel supersonically using traveling detonation wave and delivering high performance in a small volume. Volume savings also contribute to increased fuel and or payload volume, meaning that you could trade off the volume of your payload or your volume of your fuel because they're extremely efficient, providing potential range, speed, and affordability benefits compared to rockets, ramjets, and gas turbines. These are organizations that are currently studying RDE, but there's actually several thousand universities and companies around the world that are actually studying rotating detonation engines. So you see the same companies as I showed before, and the materials they use, the types of fuels. Hydrogen and methane are actually the top two choices of fuel. And you see the engine types that they're working on and the challenges, but it's all research. There's no practical rotating detonation engine available in today's market. There are generally speaking two types of RDEs, but both of them are toroidal, but they're either a continuous or a periodic type. So, and obviously the periodic type will have some sort of valve mechanism, usually a mechanical valve. But the key difference is efficiency or mixing a fuel to get the right stoichiometric ratios. So breaking them down, there's yet another 4 types of engines under that class of engines, and they are the combustion chamber shape the detonation propagation, the way that the wave travels, and the fuel injectors, which are either a gunpowder type of injector or spark plug type, which is electrical. The advantages of axial are simple design. Annular has a better combustion because of the mixing efficiency. Multiple inlets types also have good combustion, uh, and some improvement in efficiency. Coaxial, um, yeah, better control, but whether or not the efficiency is actually improved is academic. So this is a video that we have of the detonation wave, how it propagates. And then the second half of the video is to show you the demonstration of the RDE actually working. In fact, an RDE of one of our collaborators. And let me see if I can do this. No, cannot do that. So can I do this? No. Oh, I actually uploaded another one, but it didn't work. Okay. So I guess we will not be able to see this video.
Will, sorry to jump in. So you do have a couple of documents. Let me know if you need me to switch those also. Looks like you do have
Okay.
another.
Yeah,
Do you want-
I actually have this video in a PowerPoint, a separate PowerPoint.
Let me add that to the stream. We'll give this a try. Let me remove the
Okay.
slideshow for just a sec. Okay, and we'll add the video and we'll cross our fingers.
Yeah, it uploaded, but
it's not letting us play
doesn't
it.
seem to be working. So I don't. Yeah,
Okay.
what should we do?
Yeah, let me. I'll remove that one. I'll put the PowerPoint back up. Let me apologize to you. This is we're still figuring out some of the bugs.
Okay. Well, this would have showed the actual detonation wave, and it would have shown actual working RDE, in which our early designs were actually based on. So, so I looked at the TR-B because of this group, and I wonder if when the RDEs are at a distance, they actually look just like these pictures. So I don't know. I have no proof one way or the other, but our TR-B is powered by RDEs because RDEs are the most powerful engines known to man at this time, and they have the capability. They actually have the same capability as being able to lift very heavy objects with a very high efficiency of the burn rate. So therefore, technically, an RDE could actually drive these types of craft. Okay, now I want to introduce Cochrane exploration.
Thank you for the introduction, Dr. Rieken.
Yes.
I don't know, will the video play, or if not, I'll see if I can share my screen.
Does it look like it works?
Let me try something.
Tim, do you need to adjust this so he can show his screen?
Yeah, I'm trying to share the tab now.
So let me see. It looks like his slideshow is up. Yes, I think that I do need to. Do you so you're trying to show the tab. Is it having problems, Chris? Let me
No, but it looks like it's showing on my end. I just need to
try and click the present button.
actually let me stop sharing. Let me try again.
Okay, and let me see. Is there a little light bulb on it? I see one with that Raviv has added.
Yeah, maybe you can use this one if you can.
Yeah.
I'm not sure.
Would it be this one?
No, not this one, but the other one,
Okay.
the video file.
To advance science and industry into space, the world needs safe, fully reusable access to orbit. To accomplish this goal, Cochrane Exploration has been developing the CX-01 orbital spacecraft.
Chris, you want me to mute it?
This is the first iteration
No,
of
go
a
ahead.
large-scale, horizontal takeoff and landing direct-to-orbit platform that will revolutionize the space industry. It can transport cargo and passengers to low Earth orbit, as well as providing a crewed laboratory and orbital manufacturing facility. Orbital laboratories also allow the development of medications and alloys not possible on Earth.
Exploration. Our goal is to make space accessible to everyone. To do so, we need to solve some problems in our industry. High launch cost, access to only a few, vehicle safety, reusability, and accumulated space debris obstructing orbital wings. Our solution is our direct-to-orbit platform, which uses multiple engine configurations and operational modes to achieve spaceflight and other various mission profiles, such as point-to-point transport, onboard manufacturing and lab experiments, and the longer-term space exploration. For size comparison and reference, you see our Terran, Lunar, and Demo class vehicles compared to an Airbus A380. The primary difference in topologies, other than size, is the Terran class is the crewed variant of our vehicle lineup. As you can see in this overview of our horizontal takeoff and landing flight profile, we're using our methane-enabled air-breathing RDE cluster for atmospheric flight. Once at altitude, our vehicle transitions to the onboard RDE array for orbital insertion, spaceflight, and powered re-entry. Finally, this overview shows callouts for the aero surfaces, solar array, metal matrix ceramic heat shielding. You can also see the air intakes used to power both RDE clusters, which also provide fuel for the RDE array.
So thanks again for having us be a part of this. We're really excited to work with Dr. Rieken and True 2 Materials and Mir Holdings, and just using their technology to implement in our vehicle lineup. And so with that, I'm going to turn it over to Raviv Yatun, CEO of Mir Holdings.
All right, thanks a lot. And Tim, if you can move me to the slide.
Absolutely. And, I was just saying in chat, Chris, that is an amazing presentation. That absolutely, it's so powerful. This is so powerful. I mean, just congratulations.
I've got a good team working with me, so yeah, I'll thank them.
Well, and in if you're open to it in the future, maybe you come back and present on your own as well. I would love to have you present more and go more in depth.
Appreciate
okay,
that.
so let me turn things over to Raviv and. Okay, and sir, should I add this one to the stream?
Yeah, absolutely.
Wonderful. Okay, and just let me know, what you need me to do in terms of the PowerPoints and when you need me to do it.
Sure, I'm on it. I can move the slides as well. So thanks a lot, Chris. And I'm working with William together. Lucky enough to work with him. And together today, I'm going to talk about two aspects which are not necessarily connected to Chris here, but I think they are valid and important. And the first one is the ability to generate greener energy. And in that sense, we come with a great efficiency and with the ability to have less carbon footprint or any other pollution type of pollution. So we're talking about much lower emissions and a very efficient system. And obviously, we all think about going out into space, but there are a lot of problems today in our world that we may address using those great technologies. And we're absolutely thinking about the idea of generating energy using it, or even using it for other transportations, not necessarily for aerospace, but maybe even water or a ground transportation. So that's one aspect. And the other aspect is the ability, how can we actually generate energy as we move, and can we actually do some instant fuel generation? So imagine the following: can we actually go off from Earth, and while we're traveling to space on the atmosphere, can we harvest the needed gases in order to use our fuel? And in our vision, we see a situation where we actually leave it into space with a full tank. So the ability to actually harvest energy as you move through the atmosphere. We also have activity in Israel, where I live in. I come from Israel. And this is an amazing technology, and there's a lot of excitement here, and we're also planning to manufacture some of the engines here in Israel. William, back to you.
Okay, Tim, can we go back to the presentation?
Okay, sorry. And I think that's yours, right? That's your
Yeah.
presentation, Will. Okay.
Is this it?
Yep.
Oh, yes, it is. Okay, got it. Thank you. I didn't realize we were already back. Okay, so what is different about our engines and why we are already in the commercial sector is because we've been able to solve the heat problems and the other problems that rotating detonation engines that no one else has been able to solve. So we've built new engines that are more efficient than what has come before. They're compact, they're solid state design, they have no moving parts, they are recyclable, we have efficiency through detonated combustion. In fact, we have the most efficient combustion process and higher specific impulse known. Achieving more thrust with less fuel consumption, lowest in range of size of jet or rocket engines. We use laser ignitions for our engines. The small size provides more room for fuel and payload in a given airframe size. Reduced size means greater loadouts. Highest specific impulse and thrust. Let's spell that one. In industry, technology to engage, which gives technology to engage a wider range of orbits. Today's rocket technology is very limited to the types of orbits it can achieve. So with rotating detonation engines, we changed that. Far superior to normal jet or rocket engines during operation built by Pratt & Whitney, Lockheed, or even SpaceX. So we're superior to even SpaceX and Lockheed and Pratt & Whitney as far as technology is concerned. The time between overhaul and maintenance is the lowest in both rocket and jet propulsion industry. We are 5 to 10 years ahead of all competitors in delivery to market of hundreds of these engines during 2023 and thousands available in 2024. I believe we had a very nice video here, but unfortunately it looks like we can't actually do that. Perhaps next time. So what I like to show here is that we have we can of course make our engines in virtually any type of material. So, but we currently have a range of materials from thermoplastic to stainless steel, the Inconel, the titanium, and then we have nanoceramic matrix, metal matrix materials, which were developed in my laboratory. So, but what I want to show here is that we also can bring to market materials that fit into practical markets for RDEs, for different types of applications, including shipping, recreational sports, yachts, power stations, aircraft, and space applications, and more. So in general, what is a RDE? So an RDE is you have, okay. So I guess I don't have, Tim, is there a way I can point to stuff?
Oh, is there a way that you can use a pointer?
Yeah.
I am not sure. I don't think so, unfortunately.
Okay, that is fine. I will try to do it with that one. So, okay, so RDE is made of typical materials. Generally, an RDE has oxygen input and a fuel input. The fuel can be virtually any type of fuel. And then it goes up the base and into a nozzle system, which then has an igniter near there, which then ignites the fuel. The propagation of the wave is rotary propagation rather than a propagation that goes across, that goes out the thrust like a subsonic flow in a normal rocket engine. This actually has supersonic flow from the very beginning, all concentrated and focused into a central point, hopefully, because then you don't actually eat the walls of your engine. So this wave travels at 2,000 meters per second, generally. And in the case of this particular example, 500 newtons of thrust are produced for 2 to 6 seconds. And at around 7 seconds, it starts to go into meltdown. A RDE with typical cooling requires a way to cool it. Then longer time to meltdown, but less than 100 seconds of operation in general, because these things are extremely hot. So with our advanced ceramic materials, we have no cooling, and we withstand temperatures up to 3,400 C. We have multiple restart, lightweighting, because we use 3D printing, increased performance, heat management, over 200 seconds, no meltdown, and optional thermoelectric energy scavenging to support to support in any type of DC circuit that is on your platform. So we are working on engines in these ranges. So the largest is 16 centimeters tall. It's 12 to 18 centimeters in diameter. We have 3 centimeters and 5.5 centimeters and 2 centimeter diameter. In these for larger rockets and ships, you would use the larger engines. We have drones that we are working on with other people. We have also small boats and drones and other rockets. And we have kinetic projectile Mach 2 that operate at Mach 2 that are only 2 centimeters in diameter with a 10-kilometer range. So, and other types of space assets that are under development. So these are the ranges of sizes that we typically produce, because these are the most efficient sizes for this type of engine. We also partnered with established companies who design and build laser windows. These are examples of laser windows that we have been working with. We also have HIPS manufacturers, which we also work with. So these allow us to ensure that the uniform crystal structure of the engine is actually uniform. And if there's any dislocations, then the HIPS will help us to fix those problems. So currently we can manufacture 300 engines per month. They have with hydrogen, oxygen, and methane, they have a 99% efficiency of operation. And in next year, we are planning to go into 9,000 engines per month in 2024. We have our specific impulse and thrust of two material operational RDEs are more efficient. We have the highest ISP factor in the industry. The lowest ISP factor in the industry now includes SpaceX, Blue Origin, ULA, Aerospace, Rocket Lab, Boeing DSS, OSC, Virgin Galactic, the Chinese, which is CGWIC, Relativity Space, and even the United States Air Force. So I plan to have a part 2 later in the year for this presentation. So I hope that by that time a lot of the video stuff will be fixed. So Tim, back to you.
Awesome. Thank you. And actually, I am just updating our presenter instructions so that we don't run into the video issue next time. So Will, I've done some research. It doesn't look like there's a pointer tool, just so that we know for future presentations. There's no pointer, okay, unfortunately. And actually, Chris solved this. You can upload videos, but we can't do them in PowerPoints. So, you know, I'll make notes on that. Yeah, and let me apologize to you sincerely. So I think if you're all done, let me see. We have a lot of time for Q&A, but let me do this. I want to let me close down the slideshow there, and I'm going to bring everybody else back in. Let's do some Q&A, guys. But first, before anything else, I want to give all three of our presenters an enormous applause. So Dr. William Rieken, Chris Obafunwa, and Raviv Yatam. Gentlemen, thank you so much. And just absolutely amazing technology. Absolutely amazing. Again, let me apologize sincerely for the video issues. I feel like every time we feel like we've mastered something, we run into something else that we don't know. So, and Chris, again, the video that you did that's inspiring. It's absolutely amazing video demonstrating this technology. So guys, let's do some Q&A. Who wants to go first here? We can go through chat as well.
I have a question for them. I just briefly looked up what a pulsed rotating detonation engine is, and there are a couple videos on it, but I guess you guys are having trouble with your videos. Can you explain why this is putting out a higher ISP than a regular rocket engine, and what the power levels that you're achieving are, like the thrust?
I can explain a part of that. Some of it's actually proprietary, but essentially a rotating detonation engine is a supersonic engine that concentrates the energy in a very small space, given a very powerful thrust. The problem with the typical rocket engine is actually subsonic flow coming out of the injectors, whereas the RDE has the supersonic flow coming out of its injectors. So therefore, you don't see, you see our nozzle is very straight, but you realize that the bell nozzle is required for a rocket engine because it has it requires that throat in order to convert the subsonic flow to the supersonic flow. The problem, one of the biggest problems of Bell rockets is that it has a lot of multiple frequencies that are jamming each other and actually destroying the efficiency of the burn. So you only get, I believe SpaceX probably has the highest efficiency. I forgot what the number was. It's pretty good. But the typically a rocket engine is going to give you about 30 to 40% efficiency in the burn of the fuel, which means all the other fuel is just going out the back. So whereas a RDE has a very high burn efficiency of up to 99%, where, which is what I was explaining. So because it can burn such a high efficiency, it uses a much lower amount of fuel to generate thrust, whereas the bell-shaped rockets requires so much fuel just to get a percentage of thrust that would actually move the rocket. Does that make any sense?
Yeah, it does. Another thing that I saw online, this is from the people who research rockets, is that it has these rocket engines usually have pretty low specific total thrust. Is that an issue that you've come across as well?
You mean RDEs?
Yeah.
No, that's not our. That's not our. We don't have that issue at all. If anything, for the we have, for example, we have a 750 gram rocket engine that can fit in your hand, that actually outputs between 50 to 500 newtons of thrust.
Yeah, that's kind of what they were saying. 500 newtons is like 50 kilos, right?
Yeah, but it fits in your hand. Now, if you want a 500 Newton jet engine, It's about 2 meters long, about a quarter of a meter in diameter. Okay. And it will burn 30% of the fuel. So you need a big gas tank. I can do the same. I can do, that little example I told you. Fits in your hand, gives you up to 500 newtons of thrust, which is not actually, which is the same amount of power as the turbine, the jet engine that I just told you about. Now, I know this because we've already done that study on comparing the jet turbine, which is used in drones, to our tiny little engine, which can fit in your hand.
Will, I have a question for you. First off, amazing presentation. So you had two questions for it. First question, you had some numbers for how many engines. Oh, sorry. You had some numbers for how many engines you guys currently can make, as well as projected numbers of 300 this year and 9,000 next year. I have to assume that like the sizes of those engines aren't like to orbit sized, right? Those are like smaller model, like mini-sat sized.
No, these engines, we produce a range of sizes. However, the engines that we produce can actually do SSTO. And in fact, Chris's vehicle will be using those engines.
Excellent. Second question. Your payload capacity for these things. Are you thinking that this is going to be solely for orbital missions, or might this be useful for lunar missions?
I see no reason with the ISPs that we can produce with these engines that you can't do SSTO to and then move on to the moon from there. So, and one other thing is you might have noticed the thermoplastics. So the thermoplastics that we make are extremely high temperature. So we've designed a thermoplastic in which will in the $40,000 range, which will allow us to bring to the market next year an RDE which can do SSTO, which is single stage orbit, for small payloads. So that way, people who are entrepreneurs who want to start building their own platforms, their own rocket platforms to launch small payloads into orbit, will actually be able to.
Well, Will, if I could jump in with a question. So one thing I've seen in the past is SSTOs based on concept fusion drives, right? And
Sure.
is this something do you think might be integratable with that? I think when I believe it was Jarod had asked about like potentially going to the moon with this, right? And
Mhm.
the past SSTO design that I saw, this was many years ago. Dr. Paul Sis
Mhm.
had talked about that, a lunar, potentially even Martian transport, right, based on a fusion drive. Do you think that you could use the hybrid rotational engine in conjunction with something like that and switch to that once you're in space? Or
Well, I have never really looked at the problem from that perspective, to be honest. But if I was just talking off the top of my head, which I am, then I would say that why fusion drives are so popular for these things is because of the very high ISP. So, so if we already have a very high ISP, then if you need to get them into orbit, then this is the platform to do it with. So, you know, I mean, we're at least 40%, 40 to 50% better in producing thrust and impulse than SpaceX.
Yeah, well, that makes sense. Again, it's incredible technology. Thank you so much for presenting this for us today. It's absolutely amazing.
Can I get a question in? You have time for that?
Yeah, go for it, Chance.
Hi. Well, just first of all, just amazing and inspiring presentation as we see, you're kind of moving to that level of vehicles that can fly, and then I want to make sure I'm getting that right. Is a vehicle that can fly into space and return and be reusable, and you're not
horizontal takeoff and landing.
you're not dumping stages and for fuel like you do with conventional rockets. Sort of reusable aspect as well. So I can definitely see where if you're a smaller engine, your fuel utilization efficiency is higher, then more fuel will get you farther. So you do have so I just wanted to verify that this is a vehicle that would take off and land and be reusable, but can go into space.
That is correct. That's the whole objective.
Oh, that's so cool, man. All right.
So, by the way, I just want to say, thank you, Gary. I really did like your presentation. Actually, I specialize in below 5 nanometer production of materials. Actually, we're actually in the angstroms of actually atom to atom and manipulation of atoms to actually create what we want to create.
So
we can make the atoms do what we want them to do. So we actually do that every day. So I was impressed by what you had said. I had not looked at inference patterns down at the atom level like what you were doing.
Thank you. I appreciate that. Again, like I was saying before, I mean, collaborating and working together, that's the way we're going to do this stuff. So.
Well, send me an email and let's chat on that.
I connected with Chris, and if he'll share the rest of you all the email, I'll be happy to keep talking.
Yeah, I'll definitely do that.
Well, and if I could do my pep talk thing, that's one of the things. It's not just APEC, but one of the things that I'm finding is, in terms of a core community, our email list now I think is probably approaching about 2,000 people, but really we picked up probably about the first 1,000, and that's probably about the core community that's involved with this kind of research. And it doesn't mean that there's not interest elsewhere. There are tons of interest. I mean, just look at the viewership for programs like Star Trek and Star Wars, readership for sci-fi magazines and novels, things like that, right? The entire human race is interested and knows. But when you look at the people who are actively doing work in this area, it is a small, tight-knit community. And so one of my absolute hopes is just to be able to help build collaboration. I mean, I think that's so important because together we are so much more than apart, and we're out in front of what traditional organizations like NASA and SpaceX and like those are doing, and that's okay. It's fine to be out in front, but it means that we just have to rely on each other more than ever.
William, somebody has a question here. If 700-gram engine can produce 500 newtons, what size fuel tank is needed for propulsion? Would it actually take off?
Well, it depends on the mission profile and the type of fuel you're using.
Fair enough. Have you also considered doing something like Virgin Galactic, where they have an airplane that takes it up to 30, 40,000 feet and then drops it and it goes the rest of the way up to orbit?
Yeah, well, I think that idea is actually a good idea. I don't have any opinion one way or another. These ideas have been around for a long time, and I'm happy to see their success. But no, we're happy to work with anybody who anybody who wants to work with us. We're very happy to work with them. So.
Well, speaking of which, and I have your guys' emails, but do you have websites or anything like that where folks can reach out if they have more questions?
I don't.
Okay.
So just email. So.
I have a question.
Yeah, Michael, go for it, sir.
So, Will,
Hey,
I'm
Mike.
curious. When are you going to have a toy version of this? So, and how much will it cost?
I have no idea. I've never thought about a toy version.
Like a
'Cause I
drone?
want
Are you
one.
thinking of drones?
Whole nother
Yeah,
market.
like a drone.
A drone. I've killed 2
Oh.
drones this week, so that's
Oh,
scary.
Yeah, so you need to keep the price low and the parts reusable.
well, actually, one of my pet projects is pet hobbies is actually drones as well. I have DJI and Parrot, and I like them both. But Parrot has hyperspectral camera. I like that best. So, however, and it's 4K. Yeah. So,
Oh,
but
you know what? Well, I'm
I
going to
would
ask
like,
you about that.
yeah, I would love to have
So,
a drone using these engines, but I haven't found the time to do it.
So
well,
this
you're
week,
in the size range, it seems like. Can you make it smaller?
Yeah.
Is what I guess.
That's a good question, and we've partnered with some companies to look into that, but we haven't really gone through the cycle to get them all together and actually try it.
Well, that's a good way for people to learn about the tech. That's for sure.
Definitely. I look, if we make a rocket powered drone or jet, I should say rocket and jet, because this engine can use atmospheric oxygen as well as pure oxygen to operate. So we're not limited to rockets. We can actually function as a jet engine as well as a rocket.
Yeah,
So,
it would be a great toy. That's all I could say.
And for Birdie, I would say we already have a lot of operating RDEs. So when can you see it? I have another presentation later in the year that Tim and I have been talking about recently, and I'm hoping that we will do it at that time.
wonderful,
Great.
wonderful.
Thank
And
you
again,
also for your presentation.
well, and Michael, thank you. Sorry for interrupting. So we can do, well, if you want to give it a try, I don't know if you have an independent video file that you can upload. And if
I
you want
do.
to, oh, okay. Do you want to try that? Try and do upload. So if you go to the present button in StreamYard, and there should be a video file. I think that was what Chris did for his.
Okay, let me find cursor. Sorry, I've got 2 screens here. I got to find the cursor. Okay, video file. Yes.
Yeah, and then I think you just select that. Let me see. Yeah, you just select it from your hard drive. And so we may be able to see your videos that way. And again, let me apologize
Okay.
for the PowerPoint bug there.
Let me see. I'd like to show the detonation one. So
And I'm going to follow up with you on the parrot drone thing afterwards. I had one. I learned the hard way. Fortunately, it was super cheap drone. I was practicing. Do not use a drone on the beach with crosswinds. So I got it up to about 40 feet in the air. Oh, it was beautiful. I had my little 720. Again, it was super cheap drone. Little 720 video. I'm practicing with it. And then I watched as it just drifted out to sea. I have it up on my Facebook. I was just like,
What?
bye-bye, little
Oh
drone.
my God.
Bye-bye.
I'll just see. That's not cheap. I paid $2,500 for mine. That's
Yeah.
not cheap.
Yours could probably fight the crosswinds. I had a little, mine was like a $80 drone. And I did that on purpose because I have a talent for killing them. Walls, buildings, trees. So.
Okay, so Chris, I tried to upload that video and it says the video file doesn't have a video track. That's strange because it works as a video.
Question, Tim, can you play something directly from YouTube on your end?
I think so. If you want to give me a link.
Private chat.
I will drop the link in the chat and let's see. And this just kind of shows the use cases for RDEs. Hopefully this works.
Yeah, actually, me and Raviv were talking in the private chat. I'm actually flying out to Israel later this month, so I might go and meet him in person.
Amen. Hallelujah.
Okay. Oh, there we go. Okay, so Chris, let me bring this up in a separate window. And if you want, there we go. Okay, and this is called Dr. Rieken's video. Oops. Okay, and there we go. I'll put that in theater mode. I'll press play.
I don't think the audio is coming through.
There's no audio.
Oh, okay. Then we can talk over it. William, what is the specific impulse over using the same amount of fuel in a RD versus a regular rocket engine?
I think I need a lot more information than that.
Okay, like let's say you have 10 kilos of fuel in outer space. What would your meters per second velocity change be in RDE versus a regular rocket engine? It would be like 2 times more.
We don't even know what kind of fuel you're talking about.
Similar types of fuel, a hydrogen oxygen mix, or fuel being the same. What would the specific impulse increase be?
Okay, wonderful.
Okay, you want the specific impulse.
Are we orders of magnitude more powerful, or is this an increase of 30, 40%, something like that?
Yeah, if you do,
trying to ask?
Well, let me jump in really quick. So if you do have more videos like that you want to play, YouTube is easy. If you have stuff on YouTube demonstrating the effect or anything like that.
Oh. Yeah, I don't have anything on YouTube.
Like a regular rocket engine for 10 kilos of fuel puts out, X amount of newtons for that long. That will give you, a certain amount of movement through space, meters per second of change. What would a pulse detonation engine do better than that? Would it be 2 times better, 10 times better, 40% better, 10% better? Like, can you give us an idea of how much better it is?
That's not a good way to compare them. To start with, there's a lot of missing numbers here. So like I was saying in the presentation, I was explaining what we can do, but if you if you push the pulse detonation engine, and it's the right size, has all the right characteristics, then you're looking up to around 6,000 ISP for a pulse detonation engine. And there is no rocket engine anywhere that can do that.
Okay, so 6,000 ISP versus
I mean,
rocket
you're looking
engine
like I think the most efficient rocket, I forgot who makes it, is like 350 ISP or something like that.
So it's roughly about 20 times better.
Well, take it for what I just said.
Yeah,
you're
so
looking between 6,000 and around 350 for the most expensive and most efficient rocket today.
And Mark,
like
keep in mind that it is the absolute middle of the night, Will's time. So math is not probably his top thing at the moment.
Well, that's a major increase in ISP. We're talking roughly 20 times better. Raviv, is that correct?
Yes, that's correct.
Okay.
Well, gentlemen, we're at the top of the hour, actually. So why don't we do this? Why don't we give Dr. Will Rieken and Chris Obafonwa and Raviv Yatam a giant applause. Gentlemen, thank you so much. Let me apologize again for the bugs. We're still getting used to StreamYard. Still absolutely brilliant presentation, absolutely amazing videos. The technology that you guys are working on is tremendous. And Will, I would love to have you back. And actually, I would love to have all of you gentlemen back, either together or separately in the future. Again, absolutely amazing technology. So, okay, well,
it is very amazing technology, and it's something that should be developed as much as possible. So, but I'm really rooting for the little guy to get into the rocket business, and not just big multinational conglomerates like SpaceX and Blue Origin, or you don't have to be a billionaire anymore to go to space, is what I'm really saying.
Yeah. Well, Will, thank you again, sir. And so what I am going to do now is, let me see, I'm going to take everybody out of our stream with the exception of Mr. And let me see, there's Will. Okay. Mr. Jarod Yates, who is going to be presenting on the TR3B. This is something that you've talked about in the past, but again, I asked you to present on this. And the reason was, I think that this is so highly relevant, considering what like David Grush and others have been talking about. I mean, the UAP phenomena there is so much movement in that story so rapidly. I think it's good to do a refresher on the technology that may be involved with it, right? And so with the TR3B, I think as we understand things, that may or may not be a reverse engineered version of some kind of an ET spacecraft or something along those lines. But without any further ado, Jarod, let me turn this over to you. And do you have a slideshow loaded that I can use, right?
Yep.
Okay, and I'm not seeing it actually.
I could just present on my screen if you want to do it that way.
You know, I could let me see. Yeah, if you want to do that, go for it.
Okay.
There we go. Okay. Perfect.
There we go.
Perfect. Okay, well, I will mute myself out, and again, thank you again, Jarod. It's truly a pleasure and an honor to have you present on this.
Thank you, Tim. Is my audio okay, or do I need to move my microphone closer?
If you could move it a little closer, that might help.
There we go. How about that? There we go.
You know what?
Funny.
Yeah, no, it's about the same. So I would say I would just yeah. I think you're good.
I'll be comfortable. All right, everybody. Thank you for sticking around. I'm really excited to share this updated version of my research into the flying triangles. I got a lot to cover in a short amount of time, so I'm going to talk a little fast. So warp drives in the TR3B. I'm going to tell you what it is. I'm going to tell you who built it. And I'm going to give you my speculation based upon a lot of research as to how I think it works. So this project was bigger than the Manhattan Project. So we have a shared mental model of this thing. I got a bunch of pictures to show to start us off with. You can see in the middle there, the big U-safe top secret nuclear power thing. That's from Ed Fouché from 1997, his presentation where he kind of blew the whistle on this whole thing. All over the place. I got some other pictures here in the right-hand side. You can see a bunch of blurry photos like you see for most UFO stuff. Just a heads up, you're going to see a bunch of hyperlinks all over this. I'm going to share and upload this presentation after we're done here into the description of a lot of these videos. So if you want to go back, you can click on these pictures and you can track down where these videos that I got these pictures came from. So much good materials out there if you know where to look. So there's a lot of different potential models of this. There's not just one model. The one that Ed Fouché shared here, you can see it's got a width of about 61 meters. Turns out, word on the street is, there's about 9 different models, if not more, of this craft. I'm going to be focusing primarily on the 300-foot and the 600-foot width versions. There's fakes out there, by the way. You can see on the upper left-hand side there, you got this CGI thing that showed up a few years ago where it was sitting on a Navy carrier. That same CGI thing showed up in videos over Afghanistan, and then a video over Virginia. That top center image is the video over Virginia. There's a lot of similarities in these, which is quite interesting because it's pretty well confirmed that that carrier picture was a fake. And then the picture on the far upper left from Afghanistan, that one, it looks pretty CGI as well, but it looks exactly the same. So who's coming out with all of these things? I can't tell you. The upper right picture there, that's for the TR-3A, completely different propulsion mechanism. That's just a scramjet thing they came up with around the same time as another alternative airframe, but it is not the anti-gravity model. Just for a side note, that upper right image, that picture was taken in July of 2019, just a couple miles away from me here, right next to the Air Force base that I worked at. A bunch of pictures all over the place. I'm not by any means a photo expert, so I can't tell you what pictures are real and what aren't. I'll leave that up to other people, but I can point out things that look very suspiciously real for a bunch of added details. All right, so this thing made the headlines from November of 1989 to April, it says March, April of 1990. There was over 3,000 different reports. There was thousands and thousands of sightings all over Belgium. And it was becoming such a problem that they ended up scrambling some F-16s because they picked this thing up on radar, ground radar. They scrambled 2 F-16s to go chase this thing down. And they got it on radar on the F-16s, but the F-16s never made joy. They never saw it with their eyes. The thing shot off before they ever got close. And that kind of ended the whole Belgium wave incident. I'm going to refer you to David Marler. This guy is the world's leading expert on flying triangles, literally wrote the book on them. He described sightings that go back as far as the late 1800s, 1882 and 1899. These things have been around a lot longer than DARPA has been around. So for however those sightings occur, I have no explanations other than time travelers, ETs, who knows? But those aren't the things I'm talking about. I'm talking about specifically the window of time from 1980 to like the mid-90s when there was a specific program in place by the U.S. government to try to engineer a craft that could do what we've seen it do. Oh, and just one other aside on this. This graph here that I got, You can see the green line here is for discs, the flying saucers, the traditional ones, that peaked in the early 50s. And conversely, or inversely, the red line here is the flying triangles, and the rate of sightings for those go up as the rate of sightings for flying saucers go down. It made pop culture in the early 90s when X-Files came out with it, but you can see that we had already peaked in our sightings back in the mid 80s, way before the X-Files ever came out and put it into, you know, everybody's minds. This graph, by the way, comes from our APEC person, Don Tadaya. He's made a great interactive site with all of the new fork data combined into a single place where you can play with it. You can see locations and everything like that. Last side note I'm going to say about this is for the location where the majority of sightings occur for this, looks like it's around Lake Erie. So Northeast United States tends to see a lot more of these than the West Coast does. I have a video here. I'll try to play it. We'll see how it goes. This video, people try to say that it's a fake. This is the famous video from Paris from, I think, 2009 or 2011. This thing, you see a night vision version of the craft flying around, and then all of a sudden the center ignites with this ball of plasma, and it goes through these 3 resonance modes. Let's see if this works. I'm going to slow it down here. Oh, guess not. I'm not going to try too hard on this video, but the gist is that you see this plasma ball in the middle go through these 3 resonance modes. It's larger on the top than it is on the bottom in the second mode there. The entire size of the thing is slightly oscillating. And then we get into the 3rd resonance mode here. Just a moment. There we go. There's the 3rd resonance mode. It's far more spherical, but still not perfectly. And then the thing shoots off. I will say this, if you frame by frame that for the initial ignition of this thing, it has to try a couple of times to actually ignite. And when you frame by frame it through that, you can actually see the condensation on the top of the craft start following that ionization process. If this thing was CGI, that is an extreme level of attention to detail that I just got to give props to whoever faked it, if they faked it. I personally don't think that this video is a fake. Oops, there we go. This upper right image here is from BBC.com. They had some pictures that came out of the Belgian wave incident. I'm going to just focus your attention on that red ring in the very center. We're going to come back to that later, but just commit that picture of that twisting red ring into your memory. So we see the shape of that light bulb was larger on bottom than it was on top. We see that the entire size of the thing goes through these different resonance modes. It gets larger and larger. It's ionizing more and more of the air around it, or it's containing this ball of plasma. Whatever it is, the size of this ball changes as it winds up. It's also quite interesting how the size of it changes from being contained from within the craft to then extending out past the craft. Last thing, I don't have the video of this one, but it's a pretty famous one from military.com in the lower right. It's 2 triangles flying in the very center. That center orb of plasma actually oscillates in 3 dimensions. It's cavitating in 3 dimensions. There's a good number of videos out there where you can observe this cavitation of the plasma ball underneath the thing, cavitating in multiple directions while it's under flight. And the rate of that cavitation tends to be about half a second to 1.5 seconds in rate. I got to give a major shout out to one of ufology's great unsung heroes, Ray Stanford. Ray Stanford has collected firsthand data on UFOs for well over half a century. Since the 50s, he's been going out there with lots of money worth of equipment for getting magnetic readings, gravitic readings off these things, all sorts of things. He's got some good polarized images of this so you can see the magnetic fields. In this particular image, you can see these balls of plasma coming off of the thing. And I've rotated them here so you can see side by side in the bottom images there. The top half of this is much smaller than the bottom half. Just a observed coincidence and similarity between that and the second resonance mode, where we see the top half being a slightly different shape, slightly smaller than the bottom half. All right, so we've gone through the what it is. Now, who did it? From 1983 to 1987, President Reagan created the Strategic Defense Initiative, SDI, colloquially called Star Wars program. The development of this craft started before then, but SDI put gas on the fire of developing this craft. So I'm going to focus a lot on what occurred during those few years. Before I do that, I'm just going to shove a slide right in here. So this graph is the official story for the power levels for lasers that humanity has created. You can see that we didn't get to the petawatt level, the PW. We didn't hit that until about 2000. It turns out that there was an experiment done by Ed Teller down at Los Alamos National Labs called the Dolphin experiment. In this experiment, they exploded a nuke, they funneled all that energy into a laser beam, and the energy density of that thing, it was several hundred terawatts at a 1.4 nanometer wavelength. For reference, that wavelength corresponds to about 250 or 214 petahertz, which is insanely high frequency. Also, if you follow those red lines, the horizontal line there at the top in between terawatt and petawatt, that's about the halfway mark for several hundred. And you can see that the Aviation Week in Space Technology leak about this test indicates that we were at least a decade to a decade and a half ahead of the curve. DARPA was ahead of the curve by 10 to 15 years, ahead of what has still to this day been officially disclosed. So SDI, if you boil down SDI to its most basic elements, we were in the middle of the Cold War. We wanted to make sure that we could shoot down any ICBM nukes from Russia. So Ed Teller comes along and he says, hey, if we put these exploding nukes funneled energy into laser beam, nuclear lasers, if we put these onto a satellite up in space, we can shoot down multiple ICBMs all simultaneously and create effectively a complete defensive dome around our country. This was an incredible idea that Teller did not come up with on his own. There was another scientist involved that I'm going to get to here shortly. I'm also just going to put as an aside, George Shultz, Ronald Reagan's Secretary of State. He stated at Ed Teller's memorial service in 2003 that SDI was responsible for ending the Cold War. I mean, the official story is because we just outspent them, but it's an interesting comment to make at the guy that's the godfather of the space laser idea. All right, so how does this thing work? So the space laser idea was called Project Excalibur. Here's how that supposedly worked. You put a nuke inside the center of that satellite. When the nuke explodes, that energy is converted into X-rays that are focused down long crystal rods like sapphire or ruby or whatever you want to do for making the coherent beam. And it's focused such that you're able to get a directional energy blast from this nuke rather than a spherical energy blast from this nuke. There were successful ground tests of this, like I said, for the Project Dolphin experiment. The vanilla OG version 1.0, it was 1,000x increase in the brightness of the nuke. So the amount of light energy that was coming out of the nuke, because we were able to funnel it into these rods and focus it, we were able to amplify it as well. So the very first one, 1,000x increase off of the nuke. There was a 2.0 version, though, that you don't read about much. It's very lightly sprinkled throughout the SDI documents, but it was there. So the 2.0, the Super Excalibur version, was 1,000x increase on the 1.0. They figured out something on how to get a 1,000,000x increase onto this energy coming off of these nuclear X-ray laser beams. Here is an estimate I found by somebody else online who calculated it out. At the time, there was a nuclear treaty where we weren't supposed to be doing tests for nukes larger than 150 kiloton yield. So the calculation is based off of that, although if we were putting these in space, we're already breaking those treaties. So why not go all the way and put a megaton bomb in there? I mean, who knows? But these numbers, for whoever's listening and can understand them, 10 to the 20 joules per steradian for the OG version, that's already getting insane. But then they said, let's turn that up to 11, and they went to 10 to the 26 joules. That's for the 150 kiloton. You could probably put another order of magnitude or two on that if you put up to the megaton, if not more. So here's some evidence for why we need to do this. This is a New York Times article from October of 1986. The gist is that the Soviets were working on these particle beam weapons / laser weapons over in Kazakhstan at their Researcg test range. There was evidence that they were successful. Problem was their actual output wasn't high enough to be considered a threat, but the rate of progress was. Coincidentally, Russia was begging us to stop and halt all of these broken treaty experiments into these space lasers just so that they could catch up. They were about 6 years behind us with their development. So they asked for a 10-year ban that would give them more than enough time to not only try to reverse engineer it themselves, but infiltrate and send spies over here so they can reverse engineer it even faster. The US laughed at them and said, no, we're not going to stop. We see that you're doing it. We're going to keep doing it. And so we continued. And that's what I'm going to say is what ended the Cold War, is that we beat them to the punch. All right, let's talk about the scientists involved. I got 3 names for you. The first one, probably one of the most important people of the 20th century, Edward Teller, the father of the hydrogen bomb. He worked on the Manhattan Project. He ousted Oppenheimer through a lot of drama that occurred in the 50s and took over Los Alamos National Labs. He was one of the top scientists in the country for like 50 years. He was involved in so many black projects, it's even hard to keep track of. I'm going to draw your attention here to one specific conference, the International Conference of Laser Applications. This went over a number of years, but specifically the years 1987 and 1988, there was 2 scientists, the next slide will have the other scientists, where they're talking about how these space lasers can be useful for SDI. I'm going to posit later in this talk that these space lasers were actually used for development of the TR-3B. This last part is unknown provenance and veracity. The Majestic documents, if you're not familiar with them, these things were leaked in the 90s and early 2000s. People go back and forth as to whether or not they're true. I'm going to treat this one as if it's true because it supports what I got to say. So in this document, it's a letter from Ed Teller to President Reagan in 1980. So Reagan had just taken office. In it, Teller is telling Reagan that they have a vertical takeoff and landing triangular craft that pivots on its center, that would be useful for recon. Remember, the TR is tactical reconnaissance, according to most people. But specifically, he was saying that it would be useful for protection against the ET threat. There's a whole can of worms that I'd love to get into about the ET component of this, but I'm going to leave that until maybe the end, if at all. Next scientist, we have Julian Schwinger, one of the smartest guys of the 20th century. This guy got a Nobel Prize that he shared with Richard Feynman, one of the other smartest guys of the 20th century, for his work on quantum electrodynamics. He worked with Teller on Strategic Defense Initiative, at least on the sides. He also was a keynote speaker at one of these International Conference of Laser Applications, which is how I can claim that he worked with him on SDI, because that's what these entire conferences were all about, was SDI stuff. Also, he was very well connected. He attended a month before Roswell. There was the Shelter Island Conference where these 24 super high profile scientists all gathered together to share all these ideas that are not very well disclosed as far as I know. He was spotlighted back in 47 for his quantum electrodynamics work because he figured out how to boil the vacuum, essentially. Last guy, probably one of my favorites. Dr. Friedwart Winterberg is a paperclip scientist who came over in 1959. He is still alive today. He's 95 years old. He worked at the Desert Research Institute for many, many decades. It was his ideas. He's primarily involved with plasma fusion. That's what his jam has been his entire life, is plasma fusion. But he's had a lot of other interesting ideas. His ideas, though, for plasma fusion is what led to Ed Teller and the Dolphin experiment, being able to have this idea that you can explode a nuke and funnel it into a laser beam. Some of his other projects are Project Daedalus. He had the idea for Project Daedalus, which was the idea that you could have a spaceship with nukes exploding behind it, and you can ride the wave of that explosion. That one was from the 70s. He's had a lot of ideas for fusion-based propulsion, and I'm just going to make a comment here. He's got a grand unified theory that's at least worth a look at. It's at least worth giving it credit for how connected this guy has been. You should pay attention to what he says. It's about something he calls the Planck ether, which a lot of connotations there are not going to go into. His main goal in life seems to be that he wants to get inertial confinement fusion declassified, because there's so much classifications around it, especially during SDI when it was strongly developed. Still not disclosed, so he hasn't been successful. But as far as I can tell, this is a good-hearted guy that just wants the world to be a better place. Unfortunately, he's really good at keeping secrets, so he's not going to spill the beans. But if anybody is listening for any of the disclosure stuff that's been going on lately, it'd be worth getting this guy in front of Congress and asking him some questions. All right, now for speculation based upon a lot of research. How does this flying triangle manage to create anti-gravity? It's a big, bold claim. I have an abstract here that is going to be very technical, and only a few people are probably going to be able to interpret what I'm saying. So let me just blast through this, and then I'll get through all the next following slides with a little easier descriptions. You have a toroidal chamber. You ionize hydrogen or some other ionizable material in that chamber to create a plasma. You seed that plasma with a small amount of beta-decaying radioactive material. One majestic document I found suggested that cesium-147 would be good. I followed that up. Turns out cesium-147 has an exquisite branching decay chain with like 3 or 4 different decaying, beta-decaying isotopes that come out of it, which means that you're getting electrons every time this thing decays. So you seed it with this beta-decaying isotope. You then structure the plasma using its plasma frequency with RF. This is how you're going to create oscillating plasma mirrors. Those plasma mirrors are going to create parametric amplification of incident X-ray laser beams. Because these laser beams are going through the plasma that is structured, instead of dispersing, they're going to be focused, and they're going to get a twist to them, orbital angular momentum. That twist to this laser beam in the plasma is going to lead to very, very high electric and magnetic field strengths, the kind that are necessary for fusion and potentially even for metric engineering of space-time. When you exceed the Schwinger limit, you boil the space-time, you start getting electron-positron pairs, something called pair production. There's some papers out there, there's some research out there that suggests that if you oscillate these particle pairs, these matter-antimatter pairs, if you oscillate them, you can create gravity waves, you can create gravitons. That right there is the secret sauce. That's the biggest part, is if you oscillate electrons and positron pairs, you're going to be able to create anti-gravity or your own artificial gravity. All right, so to break this down, orbital angular momentum, it's a vortex. You shine a laser, it puts a twist on that laser, and because you put a twist on it, you get higher energy densities at the center. In order to create a twist on it, it has to go through some kind of medium that's going to change the phase of the wavefront of that. So instead of having pulses, you're going to have a continuous spiraled laser beam. The momentum can be transferred back and forth between the plasma and this laser beam. Very important. So whenever you take a plasma and you move the plasma, it's a conductor, so it's going to create a current, an electric current. Well, that electric current is going to create a magnetic field, which is going to interact with the plasma. So now you have a very nonlinear, chaotic thing going on where this plasma is when this plasma is moving, it's creating fields that are causing different movement, chaotic waves inside the plasma. This has been a big problem for inertial confinement fusion for a long time. So if you put a laser through the plasma, it's probably going to want to disperse. However, you are able to prevent that and instead focus it by oscillating the plasma at its RF or at its plasma frequency using RF. This is how you're going to take the natural orbital angular momentum twisting of the laser beam, and you're going to squeeze that real tight, and you're going to be able to twist it even tighter. When you do that, eventually, what I'm getting to is I think it's possible that the Schwinger limit has been exceeded. The official story is that it's not been exceeded, even though SLAC Linear Collider managed to do it in 1995 and 1996 and create 100 particle pairs, but most folks don't seem to talk about that for some reason. Anyways, it takes some very, very, very high electric or magnetic field densities to be able to convert energy into matter, which is the boiling of space-time, the Schwinger limit. That is 1.3 exavolts, 10 to the 18 volts per meter. That is almost 4.5 gigatesla. It's such high and strong energy fields that it's really even hard to comprehend. When you do that, though, space-time starts stretching and squeezing in weird ways, such that waves that would normally propagate the same in all directions now propagate one direction differently than they propagate the other direction. So when you exceed this, you start to produce these particle-antiparticle pairs. This graph I have on the lower right, take it with a big old grain of salt. The Schwinger limit is not a hard and fast limit. It's a quantum thing going on. So you've got probabilities instead. Like once you just hit the limit, you've started producing pairs, but you're not at like 100% conversion of energy to matter. So in this graph that I got that ChatGPT, unabashedly, ChatGPT helped me with this thing. So like I said, take it with a grain of salt. But the idea is at 1.7, 10 to the 18 volts per meter, you're now at about 2/3 production of energy to matter. Once you get to 3.2 exavolts, now you're about 99% conversion of energy to matter. That's probably not an accurate statement. It's just getting the general idea that as you increase, you're going to be producing more. Since it's a very nonlinear quantum probability thing, do not rely on this graph for anything other than just a mental model. In 1997, there was a propulsion conference. Teller attended. One of the guys that presented at this conference goes by the name of Froning. In this conference, he had a presentation where he suggested that you can modify gravity if you have a very highly polarized beam of some kind. He said that if you can move electromagnetic fields through a toroid with single windings, similar to Ford's rotational field, I'll describe that a little later, that's how you're going to be able to accomplish some kind of metric engineering, some kind of EM gravity interaction. If you accelerate a plasma, a lot of cool things happen, and you can actually get superluminal plasmas. Alarm bells are going off in a lot of people's heads. Nothing is superluminal. False. Some things can be superluminal. The group velocity can be superluminal while the phase velocity is not. So I'm not going to get into it too much, but the gist is that the wave front of a plasma, certain things can occur where the refractive index of the vacuum changes enough that the wavefront of this plasma is now actually exceeded the speed of light. Here's a paper by a guy from 1989 where this gets described a little bit better. When you ionize a gas, photoionize a gas, like with a laser, let's say you photoionize hydrogen. The refractive index goes from the normal refractive index of the vacuum, which is 1, down to 0, which means infinite speed of light rather than the speed of light limit of c at 1. That's a big, bold claim, but that's the claim that I'm getting towards for how this craft operates. That this moving plasma mirror, this wavefront of the plasma, is able to exceed the speed of light, and as it does so, it's Doppler shifting all of the incident laser beam frequencies ahead of it, blue shifting them, and it's increasing the energy density significantly when it does that. The scooping up of these frequencies, it's called a chirp. You'll find that in a lot of other ionosphere type research and other plasma research. Chirps are very useful for tracking down this stuff. A side note here, Dr. Winterberg made a comment about Schwinger's sonoluminescence model. Sonoluminescence is like the cavitation of water bubbles, creates like a little fusion light pulse in the center of it. And the idea is that there's some 0-point energy that might be getting released from there. So Winterberg, who deals with plasmas, said that in exploding wires or plasmas, where the permittivity is less than 1, you'll end up getting these voids in between the plasmas that ends up releasing 0-point energy. 0-point energy in this case would be the conversion of virtual particles into real particles. So these plasma mirrors. Once you get above the Schwinger limit, if you got a moving plasma front that's going really fast and you shoot a laser beam directly at that moving thing, it's going to reflect that laser beam. And because it's going at hyperrelativistic speeds, it's going to end up blue shifting it. You're going to get amplification and especially higher harmonic generation. That blue shifting means that you're increasing the frequency of this laser beam. So you're going from terahertz up to, say, petahertz, like we saw in the dolphin experiment. They're saying that this is one potential method for generating attosecond pulses of light, which is the kind of pulse speeds that you need if you're going to be dealing with fusion. Let's get into Sal Pais. If you're not familiar with Sal Pais, this guy came out a couple of years ago with a couple of patents. One was for what looks like the TR-3B, another one's for a fusion device, another's for room temperature superconductivity. He's got a lot of interesting ideas that, to me, sounds like he's either really deep on the inside or just really creative. I'm not really sure which of those two it is, but I'm going to give you the gist of what his idea is on how to create a craft like this. And it's similar, but not quite the same as what I'm going to be presenting. So to quote him from one of his recent interviews, he says that the Pais effect works like this. Controlled motion of electrically charged matter, plasma, from solid to plasma states, subjected to accelerated vibration and or accelerated spin via rapid acceleration transients. To put that into a little simpler to understand language, if you look at that picture in the lower right, you see all that shadowed edge around the triangle. That's an RF cavity where he is ionizing plasma using RF. This resonant plasma cavity is supposed to be able to eventually exceed the Schwinger limit. There's some other stuff going on there. He refuses to reveal some of the secret sauce about this stuff. My personal suspicion as to why he's doing that is because there is a Department of Energy component to this that requires secrecy, namely the radioactive stuff that we're dealing with. Department of Energy, the people who own all the nuclear stuff, they really don't like it when people play with radioactive things for good reason. Ed Fouché. So Ed Fouché is the whistleblower that I spoke about from 1997. He gave a bunch of talks on his experiences with interacting with the flying triangle down at Area 51. After he had talked to a bunch of his coworkers down there, he eventually was able to glean the following information about how this thing worked. He said that it was a plasma that was mercury-based, that was pressurized extraordinarily high at 250,000 atmospheres, 25 gigapascals. He said that it was operating at cryogenic temperatures of 150 Kelvin, that's negative 190 degrees Fahrenheit, negative 123 degrees Celsius, and said that it was accelerated to very high speeds, 50,000 to 60,000 RPMs, which for a 600-foot model, that would equate to about 575 kilometers per second, or equivalently, if this was a toroid donut around the edge of that craft, that'd be about 1 kilohertz frequency. A side note that I must say, many of the people who have witnessed this craft describe a audible low frequency emanating from it, somewhere in the range of 400 hertz to 700 hertz. So the fact that Ed Fouché's numbers here come out to about 1 kilohertz quite coincidental. So if it's supercooled plasma that's mercury based, that means we're dealing with a superconducting mercury plasma. I did my homework. I found a paper out there from mid 2010s, I think, where they were experimenting with different mercury based cuprates, superconductors. And it turns out, here's something really cool that I go back and reference constantly. If you look at these red lines in the upper right graph there, these red lines are Ed Fouché's numbers. If you notice Hg, mercury, 1212, that particular test at the pressures and temperatures that Ed Fouché describes is right at the edge of the phase transition of the critical temperature, right on the edge. It's very important here, and here's why. Ed Teller released a paper in 1976 called Electromagnetism and Gravitation. I cannot recommend this paper highly enough. It's only like 2 or 3 pages. Definitely worth a read. There's a lot of unspoken nuances within. One of the things he describes in there, though, I'm going to quote it directly. If the crystal has no ordered permanent dipole moment, but we're near the phase transition where such a dipole is established, the rotation will produce big effects which go off to infinity as the transition temperature is approached. In this paper, he was talking about electrets, which are electrically polarized materials. There are certain nuances to that. You can treat a plasma under certain conditions as if it's an electret. So at the beginning of this talk, I said that you needed to pay attention to that red ring that was on the underside of the flying triangle from the BBC picture. If you look closely at that, you can see these curved filaments coming off of it that strongly resemble that tokamak winding right next to it, which is the same geometry that Robert Ford from Hughes Research talks about with his idea back in the 60s or 70s about Ford's rotational field. He suggested that if you pumped a superconductive liquid mercury through those pipes at the same time that you rotate the entire apparatus, you should be able to generate extreme electromagnetic forces that reduce the mass and eventually are able to create their own artificial gravitic field. Very interesting overlap between the BBC image and Ford's idea. So we keep talking about superconductors. What's the deal with all these superconductors? Why has it got to be superconducting? Turns out, there's more papers out there. When you use a superconductor, you are able to lower that 10 to the 18th volts, that exavolts requirement, down to the 100 megavolts requirement. I'm going to go into reasons on how that happens. We got 3 people here. We got Ed Fouché at the top, we got Sal Pais in the middle, and we got Eugene Podkletnov at the bottom. If you're not familiar with Podkletnov, he had a rotating superconducting disk that he slapped with some megavolt, 2 to 5 megavolt charges, and he described 2% weight loss. So we got all these guys talking about superconductors, while Pais is talking about fusion and Schwinger limits. The idea is that when you have a superconductor, you have these things called Cooper pairs. The electrons pair up. Well, when the electrons pair up, that means that now as they're super highly energized in the superconducting plasma, you're starting to boil space-time. You're converting those virtual particles into actual electron-positron particles. It doubles the number of those because you've got Cooper pair doubles to begin with. Also, superconductors have a much reduced band gap, that tunneling gap required to cross energy levels. So there's a band gap between the virtual particle scene and the real physical world. That band gap is normally 10 to the 18 volts. Superconductors have a much reduced band gap. They are reducing that overall tunneling requirement from 10 to the 18 down to 10 to the 8th. Well, if they reduce it down to 10 to the 8th and Eugene Podkletnov reduced it, or Eugene Podkletnov was dealing at about 2% of 10 to the 8th at 2 to 5 megavolts, and it just so happens he described 2% weight loss, coincidences arise. There's a couple different ways that you can try to achieve this boiling of the space-time vacuum. I just described how you can do it with superconductors. Here's what happens when you include lasers into the mix. Normally, if you just shine 2 oncoming laser beams at each other, very high energy. The photons from those two will collide, and in that moment of collision, the energy will exceed the Schwinger limit, and you'll get particle pair production. However, there's something called the nonlinear Breit-Wheeler process, where instead of slamming them into each other, you just have an extremely highly strong energy density field, like the plasma field. Instead of that lower picture there says laser field, replace that with plasma field. Now you shine a photon through from a laser, and you've already now reduced the amount of added energy that photon needs to have to be able to exceed the Schwinger limit. Side note, last year there was a team with Dr. Newth. They went down, they were called UAPX. They went down to Santa Catalina Island down in California. They spent a week down there with a bunch of different measuring equipment. And while they were down there, they observed a few different UFOs. They measured a few different UFOs. One of the best measurements, they saw one off the coast. It was a couple kilometers away, and they got triple repeating gamma ray bursts. These are gamma ray photons, by the way. Triple repeating gamma ray bursts, and the highest energy from one of these bursts was about 43 MeV, which is a lot. If you wanted to create that with an electron gun, it would need to be 10 meters long, and it would need to have a 4.3 megavolt per meter electric field, which is a lot. You're only going to get that with plasmas. So we've talked about these electric requirements. What about the magnetic requirements? Well, we come to Dr. Winterberg and another one of his papers. This one was, I can't remember when this one was from. I think early 80s or early 90s. Anyways, this one, the idea is that you ignite the plasma. The plasma extends both directions down this donut. And as it's going down there, those arrows that are tangential to the tube, they are magnets that are squeezing the wavefront of this plasma. So as you squeeze that wavefront, it accelerates that wavefront up to relativistic velocities, like I've been saying. What's cool is you get a Lorentz contraction of the front of this plasma wavefront that ends up increasing by orders of magnitude the magnetic field strength of that wavefront. He says that you can get thousands of Tesla, 10 to the 3, thousands of Tesla by doing this. Remember that number, because in a couple of slides it's going to come into play. Thousands of Teslas. Here's a more one-dimensional view of that same idea. On the far left, you have a mirror. You ignite the plasma, so it bounces off the mirror and continues over to the right side of the image. As it's going through there, those little slashed dots on the bottom are little electromagnetic power supplies that are switching closed in succession so as to accelerate that wavefront. Like I said, you can get thousands, you can get orders of magnitude increase in the magnetic field as this thing reaches relativistic velocities. Going back to Ray Stanford's images. So in 1980, Ray Stanford took this picture. He actually was videotaping this with an 8mm camera that had a polarizing cube on it. So it split one half of the polarization of the light to go up to the eyepiece, and it split the other half of the light into a different polarization that went down to the tape. When he was watching this through the eyepiece, he didn't notice anything, but upon going back and watching the film, he observed these rings coming off the corners of this craft. These rings are called Faraday rings. When you have polarized light that goes through a polarized medium, you end up getting this diffraction going on. And by counting the number of rings, you can try and estimate the strength of the magnetic field. Now, because there's probably a very strong electric field in play from the ionization going on, it's really hard to estimate, especially without good color photos. It's hard to estimate the actual magnetic field strength here, but I can at least get it within the ballpark of somewhere between 50 to 5,000 Tesla based upon his distance away from this craft, the altitude that he was at when he witnessed it, and the total number of rings. Highly recommend looking into Ray Stanford's work. I cannot recommend that enough. Also, he observed this in 1980. Let's just track with the timeline here. 1980 is 3 years before SDI, and here we got triangular craft with similar magnetic field strengths that Winterberg was describing. Oops. All right, another important paper, and this is one of the most exciting parts, I think, of this entire talk. Ed Teller, 1992. Ed Teller leaked like a sieve. He said all sorts of classified material in not so classified settings that MJ12 was very not happy with, but not a lot that they could do about it. So in 1992, Ed Teller proposes this fusion-based propulsion device for long duration space missions. I'm just going to focus your attention here to two things. First, look at the lower right image. Notice how we have these cryogenic temperatures, 4.2 Kelvin, 300 Kelvin, 900 Kelvin. We're not quite at the 150 Kelvin, but let's safely assume that he probably adjusted some numbers so that he didn't actually get ganked by MJ12. But also, in addition to that, notice those vertical bars on the lower half of the circles in that image. Those are the MHD, magnetohydrodynamic generators, which that research is all throughout SDI. They figured out how to be able to use this plasma to generate energy to be able to then cool the plasma. They cool that plasma. That's a superconducting magnet or superconducting plasma. They're in the center where a lot of the magic happens. Now for the really good part. Figure 3 from this paper. On the leftmost image there, where you got the same circular image from figure 9, you can see we got this egg-shaped magnetic field going on around this device. Side by side, I got Ray Stanford's image there, where you can also see it's kind of egg-shaped. It's a little hard to see, so let me go on to this one, where I'm going to go back and forth and just overlay them. So we got the egg shape of Ray's pick, and now we got the egg shape from Ed Teller's paper. Also, note the sizes of Ed Teller's graph here, how we're talking in terms of, a couple of meters for the heights and the radiuses of these rings. I'm just going to leave it open to speculation as to how large these rings from Ray's pick are, but I bet you dollars to donuts it's the same size. Last thing from this paper. In Ray's picture there, you can see we got these clouds coming off underneath this thing. Figure 4 from Ed's paper. Note at the top there, we got those egg-shaped magnetic fields and how those end up ionizing stuff around them. And that ionized material then gets ejected beneath it, as it's also getting neutralized in its charge. That's part of the whole neutral particle beam stuff from SDI, if you're interested in that. Anyways, you're able to use it's not even exhaust, it's just the surrounding medium. You're able to use the surrounding medium as additional vector potential, which is fascinating. I mean, talk about efficient. All right, putting it all together. I put a lot out there for y'all. Here's what it is when you put it all together. You ionize a plasma with a really strong laser. As that ionized material becomes a plasma, you start accelerating that wavefront of plasma up to relativistic or even super relativistic speeds. It then ignites some fissile material. You create some fusion. Once you have fusion, now you got enough energy that you can start really going to town. You can use these relativistic plasma mirrors with instant laser beams at approximately 400 to 1,000 hertz of instant laser beams hitting these plasma mirrors. You're going to get parametric amplification of that laser, and you're going to start creating particle pairs out of the vacuum. Then you're going to oscillate those particle pairs to create gravity waves. And just for added benefit, if you're flying around an atmosphere, you can use the ionized atmosphere around you with these magnetic fields as additional forms of thrust. This thing's been secret for a really long time, even though we got leakers coming out. There's still no official document out there that says, yes, we have this craft. And apparently, if it's been out since at least 1980, we're going on over 40 years this thing's been out, and it's still so classified they can't tell us anything about it. What's going on with that? Well, I have some speculation for you. One, nuclear fusion would completely eliminate all need for, well, not all need, but all of the petrodollar value And as we can see from Gulf War I and Gulf War II, the military-industrial complex seems to care a great deal about the value of oil, specifically because the entire U.S. economy, and thus all of their funding, relies upon the value of oil. Additionally, this thing has capabilities that are so extreme that to even disclose these things could provide a potential benefit to adversaries. So they don't even want to let the adversarial nations know that we have this, because then they might be able to try to start doing it themselves. Additionally, and going a little more into the conspiratorial element, UFOs, UAPs, that majestic document from Ed Teller suggested that they actually needed to develop Excalibur space lasers to be able to fight not terrestrial-based threats, but extraterrestrial-based threats. And the need was to eventually put a neutral particle beam weapon onto a platform that could keep up with these incursions of extraterrestrial vehicles that are hostile to all of us. So you can try to drink the military-industrial complex Kool-Aid and say that they've actually been protecting us. The military's been protecting us for a very long time by keeping us in the dark about the fact that we could all be eliminated in the blink of an eye by an advanced civilization, and it's only through their efforts of SDI that we're even still here today. I'm a little torn on that. As a veteran, I tend to lean more towards trust in the military, even though there's plenty of stuff that suggests it shouldn't, but overall, I tend to do so. Lastly, those neutral particle beam weapons, those things have energies of damage as great, if not greater, than nuclear weapons without the fallout. That right there is like the golden sword for all of the adversarial nations. Could you imagine Kim Jong-un or some other, crazy world leader with the ability to fly a craft across the planet in a couple of minutes, blow up whatever he wants with the energy, the amount of a nuke, and then fly off, and he's in and out within a couple of minutes? That's the kind of nightmare scenario that is why it necessitates secrecy. All right, wrapping it all up for you. So the TR-3B, I'm saying that it uses one, potentially both of these mechanisms. It's using hyper-accelerated, ultra-relativistic plasma mirrors with instant laser beams to create particle-antiparticle pairs, which are then oscillated to create gravity waves. That's a field-based propulsion device. You're not actually emitting anything. However, if you're in a medium such as atmosphere, then you can use that medium as a propellant with the neutralized particle beams that are coming off of the edges of this craft with strong magnetic fields. Here, I got a bunch of links I'm going to leave up on the screen for a second for anybody who, for whatever reason, doesn't have access to this slideshow. You can just type these in, pause and type them in. On the left there, those are the slide numbers so that you can follow up and go back through. And then there at the bottom, if you need to just type it in, there's the link to this presentation at the very bottom. Also, there is an exquisite TR3B playlist that I have for you there, also at the bottom. If you want to get in contact with me, my YouTube channel is Massive Yet Tiny Brain, Mighty Brain, and the email for that is mightybrain@yahoo.com.
Wow, Jarod, I don't know what to say. That is amazing, absolutely amazing. So let me do this. I mean, first thing, I'm going to add everybody into the stream. And I think that we need to give you an enormous applause. Mr. Jarod Yates. I mean, the original TR3B presentation that you did was stunning. This is just amazing. In fact, I was taking notes. I'm going to be doing some follow-up on a bunch of these. Friedberg Winterberg is definitely towards the top of the list there. So, well, so do you guys want to do, I mean, we've only got 2 minutes left until our lab partner time, but do you want to spend maybe 10 minutes or so and do Q&A? You guys want to do some Q&A? Let's do that, because I'm sure I haven't been looking in comments here. I have lots and lots of clapping.
I see one question here that looks pretty good. What material is the plasma coming from? So we see that Ed Fouché said that it was mercury based. We see a Majestic document that says that you need to seed it with beta decaying radioactive material. We saw temperatures in that Ed Teller paper towards the very end that suggests that they were actually dealing with hydrogen. I can't tell you for sure exactly which material they're using to ionize it, but what I can tell you is that if you go through the SDI MHD papers, which primarily are geared towards naval propulsion and scramjet propulsion, that in those papers, they talk about all these different materials that they were using to try to create these plasmas for magnetohydrodynamic generators. So it's in there somewhere. Other than speculating that it's hydrogen, I can't tell you.
You know, Jarod, if I could jump in. So one of the questions that I had was, you had mentioned someone telling President Reagan that there was a triangular craft that basically described it as the TR-3B. Are there notes that people could follow up on if they wanted to research that further?
Yes. So in those links that I provided towards the end, you can see that the website. You can follow that link to the website, which is majesticdocuments.com or something like that. And they've collected all of these documents together in one spot. And it's fascinating. It is a trip to read these documents. You got to take it with a grain of salt, like you should with all of these tinfoily type things. But I would really like to mention something important specifically about that document and how it ties in with other similar stories around the time. So my personal belief in the speculation as it sits today is that there has been a ET threat among us for a very long time. That was part of the reason for the creation of MJ-12. It wasn't just so we could reverse engineer technology. It was because there was evidence that these aliens, when they were turning on the Russian nukes, that they were a direct threat to the existence of humanity. And that there was a small clandestine group of people that were protecting humanity, not just by keeping them in happy, blissful ignorance, but also by trying to create deterrence for these things. Just trying to blow up a nuke isn't necessarily enough to be able to defeat these craft. Additionally, if you take Ingo Swann's word for it, he's claimed that in 1976, he was recruited by some small group, I think it was MJ-12, recruited by them to go do remote viewing on the dark side of the moon. And he saw large bases over there, and the military individual that was, recruiting him for this was very concerned about this. I suspect Excalibur, as well as the TR-3B, may potentially have actually been our military response to a threat that this group couldn't even disclose existed. And I don't know to this day whether or not that threat still exists. If it still does, that would explain a lot of the, hesitance for disclosure. But the space lasers plus the space plane that can do warp speed, you don't need that for Earth. You need that to fight the aliens. That's what the Majestic documents, anyways, are suggesting.
Yeah, it's, again, absolutely amazing presentation. Jarod, thank you so much. And again, I'm just putting up, lots and lots and lots of applause. I'm not seeing, well, let me see. Jake Hunnard asked, so Teledyne, Ryan sold the rights to their flying triangle to Lockheed, I guess. No?
I don't necessarily know that I would ascribe to any one particular government contractor, military contractor, the ownership of this craft, at least for the years of SDI. Those contractors were used to help develop certain components of it. I believe it was Northrop Grumman helped develop the frame. Lockheed Martin helped develop some of the fusion. But most of that research occurred in national laboratories, far more than it occurred in, S4 hangars. Eventually, though, especially I suspect, we probably ended, once again, major speculation, take it with a grain of salt, but I suspect the ending of the Cold War, Reagan was all about, hey, can't we just put all our differences aside if there was like some ET threat? It could be that there was an ET threat that we did eventually defeat in some meaningful way, or at least neutralize. And then in the 90s, they were trying really hard to disclose this. Ed Teller was trying really hard to disclose this. Winterberg was trying really hard to disclose this stuff in the 90s. And they got blocked at every single step of the way, just about. So from that, this technology, eventually this group of protective individuals kind of, changes hands and ideas of what their role should be. As they did that, now it starts changing. This tech starts changing hands to the different government contracting agencies, and that's where we're at today with the disclosure-esque stuff that's going on. Is, well, which agency owns this? Does Raytheon have this stuff? Does Lockheed have this stuff? Who's got the goods in the hangar for the reverse engineered stuff? Not even speaking about the actual recovered stuff.
Yeah. Well, Jarod, so I have a couple also from Paul, and Paul was asking, he actually had two questions. One of them was, what is the material forming the plasma from? He had also asked about mercury in a separate question. And from Stan Deo, I think, had talked about something similar, and in his case, mercury was the plasma material, right?
All right, so I kind of talked about this a little bit. I'll go a little more in depth. So the original flying discs, the Vimanas, the D Glock, the Nazi Bell, all of these things, they always talk about using mercury for some reason. The best evidence for use of mercury that I can find is if you use an isotope of mercury that has a beta decay, you can get increased electrons coming out. These increased electrons are increasing your overall charge density, which is going to help you slowly start to achieve this Schwinger limit, right? However, mercury is not the best one to use for this. It's got a crummy decay branching chain. You want to use something that's got a decay branching chain that is much faster and many more steps of decay, each with beta decay occurring every time, as well as eliminating alpha decay, because alpha decay will end up quenching this stuff. You don't want that. So that said, that's why they came up with the cesium idea. I'm not super sold on the cesium, but it's the best that I got to go on for now. The mercury stuff that's last year's news. You don't need mercury stuff. Don't deal with mercury. There's much better radioactive material out there that you can use. Also, final thought on it. When you accelerate this radioactive plasma really fast, you get that Lorentz contraction. That means that wavefront is experiencing time at a different rate than we're experiencing time as the observer, right? That means that it will decay at a different rate than if it was just traveling at observer speed. So if you have something that decays in 100 milliseconds normally, and you accelerate it super duper fast, it's going to decay at a slower rate relative to us until, bam, it slams into something, or it stops, or it gets hit by a laser. And then now that momentum transfer is going to change its velocity. You're going to get a way different amount of beta decay coming off of it. A spray of electrons from this beta decay is all going to happen when it decelerates super fast.
Okay, and that was cesium-148, right?
47.
147.
You only can create from nuclear explosions anyways.
Okay, well, there we go. Does anybody else have any questions? Let me see. Anybody in our audience here? Mark, Jeremy, Chris, and let me see. Michael is there. Michael is out of camera, though. He's hiding.
I have some comments, but I don't know if you guys can hear me well, because we have the machines turned on behind me.
Yeah, I can hear you.
So one thing I wanted to mention to Jarod, I know you look at it sort of as an alien threat, because they turned on they put the rockets in Russia to the ready mode. In America, what they did was they shut it down. So I think that has more to do with the Russian mentality versus the American mentality. They wanted to scare us both off, but to do it in Russia, what they do is they're arming the nukes, like, hey guys, you're about to blow yourselves up. And in America, they're like, no, you guys are not going to be able to control this. We'll take it apart. And I've actually heard of a story, and take this with a bucket of salt too, that a gray alien materialized in one of these nuclear facilities and took apart a detonation device in front of a bunch of officials, and then like disapparated Star Trek style, as one of their screw you kind of things that they're showing us. But in Russia, with a different mentality, different culture, the way to do that was to arm them, freak them out, and say, hey guys, you shouldn't be playing with this.
That's really interesting. One added thing, if I might put out there. So I was using it as one particular example. I suspect that there have been many examples out there of how they presented themselves as a threat or as untrustworthy at a minimum. One other example of their untrustworthiness, supposedly, bucket of salt, there was a interaction between President Eisenhower, Ike, and some gray aliens, where they came up with some kind of agreement, because we weren't okay with them just, violating our airspace willy-nilly all they wanted and going and scaring people and maybe even revealing themselves in ways that we didn't want. So there was an agreement that was made. The story goes that supposedly they wanted to be able to understand our genetics better so that they could do all sorts of stuff to help themselves with. The agreement was that we would provide them with cadavers, dead bodies. They can do all their genetic testing on the dead bodies. They reached that agreement, and then shortly thereafter, the aliens broke that agreement and they started abducting people. If you look through all of the abductions of people, there's plenty out there that are not good abductions. I mean, the Betty and Barney Hill one is like the most famous, but there's a lot of stories out there. Final part on it, some of these actually result in human mutilation. That's the scariest side of all of this, is if you look into human mutilation from alien encounters, there's some bad stuff out there where it looks exactly the same as cattle mutilation, except done on human bodies rather than cattle.
Okay, so I think that probably concludes our presentation for today. We'll end it on the human mutilation note. So everybody, let's give Mr. Jarod Yates again an enormous applause. Jarod, thank you. I think people should probably stop and reflect for a moment on the amount of research that it takes to do those presentations, right? And this would apply to everyone who is up there, because you guys all do presentations, right? And I know Jeremy has done he's done many that are the same as well. And Mark is in his lab doing research right now. But the amount of work that it takes to go through and collate and organize all that information and follow up on all of that is just tremendous. It is tremendous. And so, thank you so much. Okay, well, so guys, why don't we do this? Why don't we go into our lab partner time? And I will bring in Mr. Brian Sinclair as well. Well, what we should do first, though, probably, so for lab partners, again, the idea here is, since the beginning, APEC has been about building things, right? And it is wonderful to have theory and ideas. I personally love big picture stuff, but APEC is all about hands-on building stuff. And I know you guys are all building stuff, so there's, that works. Who should our first victim be? It should probably be Mr. Sokol, I think. And I use victim in the most polite, loving way possible, Mark.
Okay.
Okay, so let me make you the solo presenter. I'll remove everybody else out. Okay, and go for it, sir.
Okay, so Jarod was going on about tinfoil hat conspiracy theory over here in Falcon Space. And I'm going to be screaming because there's a lot of noise behind me. Tinfoil hats are actually our standard PPE. When we turn this bad boy on, X-band wavelength, if you don't have some sort of metallic thing protecting you, you can get hurt by the microwaves. Although right now they're going into a Faraday cage, so it is pretty well shielded. But when this device is out here in the open and we're testing stuff, the microwaves can get pretty strong. So what you're looking at on the screen around me is several cameras of this experiment, and I want to run you guys through noise floor issues that we've been having, and some of the things I've learned about X-band microwaves and how you have to deal with them in order to run this experiment. Again, for those who don't know, this paper, Anti-Gravity with Present Technology, Frederick Alzafon, we're running that experiment. He's got a theory. Everyone who's read the paper and saw the experiment came up with their own theory. So if you don't like his theory, I'm sure you can make up your own as to why this would work. So far, there's like 5 or 6 theories going on about it. Essentially, what we're trying to accomplish is dynamic nuclear orientation, which is spin orientation on a subatomic level. And to do that, we're using electron spin resonance, which is basically a magnetic field, and RF in the range of gigahertz, which tickles the valence electron, which then, through the hyperfine coupling, goes to the core of the atom. So we had Dr. Keith Earle down here, Professor Keith Earle from Albany State University. He recommended, amongst other things, as a form of a sample, to try to get polarized metal, aka metal that goes through its transition from liquid to solid while it's inside of a magnetic field, something I've been contemplating as well. So we have our magnetic field and 3D printed some plastic over here. We then covered it in, this is basically like a mold. We made a mold out of it, and then we burnt out the center, and that leaves us with a hollow space where the plastic used to be, and the plastic just burns away. And then we were able to cast these nice little aluminum pucks out there. And you can see in this corner over here, there is some nice crystalline growth that happened. That's because we were heating it as we were doing it in order to have it cool slower in order to build up a crystalline structure. Well, that's the sample side, but the experiment side is a lot more difficult, because when you're trying to get microwaves into a metallic sample with a certain geometry, it doesn't work very well because the sample itself needs to be tuned to the wavelength in a very particular way, which we're still trying to figure out. Another issue you have, EPR and NMR are mostly done with non-metallic, non-conductive biologicals, and I spoke to one of the top experts on it the other week. He said he's never tried it with metals before, only powdered. He recommended we try powdered lithium inside of an epoxy or something like that. So we have a lot of samples yet to run. But let me run you guys through what it is you're exactly looking at on the screen around me. So to my left over here, that is the weight of the current sample we have inside the chamber, and you're getting a live view of it. So 0.98 grams, 0.97 grams. It's shifting around a little bit. This is our noise floor, and part of the noise floor problem is air currents. Tom, you want to give them a demonstration? Yep. Tom's right next to me. He's going to walk past the Faraday cage, just give you an idea of what can happen to that weight change. So we just dropped down like half of a hundredth of a gram, so that would be like 50 milligrams change, and that had to do with the airflows as he's going back and forth. So that's an issue we have to overcome. There's also an air conditioner in the area, and we can't really shut that off because the equipment behind me that produces the RF gets pretty hot. So unless the air is running, so we're thinking of putting up a door over there to stop that issue. Above it, you have the weight of the entire chamber. So the way we did this is on the electromagnet on my, on this side, I don't know how it shows up for you. You'll see there's a bluish sort of joint. It's up against the magnet. That's actually a very loose connection that can twist on its axes right there. And since the test chamber is offset, we're able to get a weight measurement by just holding it from that joint from where it connects. Another thing we found that's very important is in order to get maximum resonance, you need to isolate the chamber from the waveguide, from its ground. So it needs to be floating, electrically floating. And in this current configuration, we're trying what is called the transmagnetic 110 mode. It's basically a 1-inch piece of copper pipe that you use for plumbing, and it resonates at 9.88 gigahertz, roughly. And the feed point is from the side. So I'm going to turn on the RF right now, and you'll see another issue that we've been having. By the way, the black with the squiggly lines down there, that is reverse power coming back from the chamber. So we have a circulator, which energy that comes in here goes out here, but energy that's coming back will end up in here, and it goes to a detector, which then shows up on the screen, which is then shown on the screen over here on YouTube, the little black screen that's below me. So you'll be able to see what the reflected power looks like. We also have another oscilloscope over here that I didn't attach to this whole data collection system that shows us what the RF in the room looks like. That's just another connection point. We can connect it to different points within the RF system and view it from different angles. View what the RF signal looks like. Again, these signal spectrum analyzers are reading electric modes, so they need to be offset in order to get that. The sample for dynamic nuclear orientation only cares about the magnetic mode. It'll be the magnetic field going through the sample, perpendicular to the magnetic field of the static field. So we're going to turn on the RF. Now the amplifier is on, and now the RF is on. So the reverse power is about -2 dBm. And you see how there's a nice triple mountain setup over there. If I move the frequency around a little bit, you can see really interesting things happening. So this is when you're just out of tune and it's like it doesn't really like it. This is when you're close enough, but you really want to minimize the amount of power that is coming back. The lower the power, the lower the reverse power, the more power is staying inside the chamber. So that's the key to this section. And right now we're at 9.8801 gigahertz, and it's at -3 dBm. So we did get a slightly better coupling by dropping it. Oh, yeah, just went a little bit too far there. Next thing we do for these experiments is we turn on the magnetic field, which we have controlled right now by an Arduino that can put the magnetic field through its paces. It can start at whatever Gauss you want and go up to whatever Gauss you want. So that's going to be turning on momentarily. Yeah, right now we're about 2,000 Gauss, and that's the starting point. This experiment, as it is right now, will typically run for a couple of hours, and we can stay out of the lab and come back and look at all the data. But there's a couple of problems that we're having. Notice the black screen below you. You see those little spikes that are starting to spike up? So what happens is, after this is running for a couple of minutes, those spikes start to fill up the entire space, and instead of getting these nice sharp domes, we're ending up sharp spikes of frequency. I'm getting a much broader, like more of a noise generator effect. And this is over, that's 168 megahertz is the entire span. I could zoom in on its span. Okay, now I zoomed in. We're at 100 megahertz right now for the span. You'll see it start to build up. What we believe is happening, and this is a conversation I had with Todd and some other RF engineers earlier, is that the reverse power is too great for the amplifier, and it's starting to heat up, causing these weird effects. So what I think we need to do is add in some more shielding, or what you could basically do is you can use this same device, the circulator, to take all the reverse power and absorb it as heat energy so it doesn't go back. And that's what we have this moving load for. So I think in a future iteration, we'd be adding on some more Lego to the device in order to get a more coupled load. And there you see it. The waveform went from a nice sharp edge to a more broadened edge signal, and the entire spectrum that you're seeing is 100 megahertz. So that's probably plus and minus 30 megahertz that are being pulsed in there. So it's not a very sharp signal that's going in at this point. It only lasted for a short amount of time. Now, if I were to shut off the amplifier, allow it to cool for a little bit, turn it back on, sometimes I get the nice sharp edges back. Sometimes it takes a little bit longer to get that. But I know for certain it's not coming from the spectrum analyzer. It's probably coming from the amplifier or the signal generator. Okay, so the next thing we're going to talk about, let me see if I can, nope. It needs to cool down a little longer. The next thing I want to talk about is the data itself. So the data we've collected so far is inconclusive, although we have seen some interesting dips at expected points. I can show those to you right now. Let's see if I can present. I'm going to have to do a share screen, so let me pull this up. Share screen. Okay. So this is what some data looks like from a typical experiment. This was experiment number 1, or 62023A, and we're going to kind of shut down some of this stuff right now just so we have a little bit less background noise. Shut that off as well. Okay, so it's a little quieter. So this experiment, 62023A, that's the date, and A meaning the first one of the day. Gauss range was 2000 to 4940, and then there's the frequency. We expected to see a dip somewhere in the center, and there is sort of a dip. But again, this was with a 2.62 gram sample of aluminum that was polarized in a magnetic field and covered with ferrofluid. It's actually, sample is right here. This is the actual sample that was used. And this was haphazardly made. The shape of it is not very geometric, so we were having a lot of issues getting any coupling to it. In a couple of these instances, I had to change the frequency between each run to try to find a dip. So in experiment A, we see a dip roughly over here. B, we see a dip roughly over here. But this is a very noisy signal. We need to get something better than this. And in C, it rose up a bit. It moved over. And we can also see in the data that there is an increase in the frequency ever so slightly in order to take over for the untuned chamber because of the sample. When you stick the sample inside the chamber, the tuning of the chamber changes a bit. That's actually the reverse signal that comes back is actually how you measure NMR or EPR samples. Here's some further data. We keep on seeing dips everywhere, but again, I think a lot of this has to do with airflow that's in the lab, especially the really sharp stuff. So when you see like a gradual thing, this is occurring over the course of 20 minutes or so, or 10 minutes. That's not me or Tom walking by. By the way, we do run these at night when there's the minimal amount of street traffic as well. And you can also tell the times between them. This one started at 6 p.m., ended at 8:21 p.m. But we plan on doing these more overnight, and Todd is helping us with the programming to get a system that can just run it 4 times, over the course of the night when there's minimum traffic in the area. We can just get a whole bunch of data and then, zoom in on the blips from there. On June 21st, we wanted to do something a little different. Todd recommended we put the sample at the very edge of the field. Now, being at the edge of the field, because this one also had, I believe it had some covered in ferrofluid, yes. So this was slightly ferrous. It will be attracted to the magnetic field as the magnetic field strength increases. So what you're seeing over here, the increase in weight, that was expected. What was expected for a positive result will be these little blips over here. And let me see and see, what did we change? I drastically changed the frequency over here. And this might be showing something interesting, because when I changed the frequency, and this was a noticeable change, you can see these 2 blips over here, and they sort of move down this way. If I'm interpreting that right, I'm not sure. But because the frequency was dropped, the blips would move down the magnetic field, because it's a correlation between strength of magnetic field to RF frequency. You can do these sort of experiments with almost no magnetic field and very low, weak magnetic field and low frequency, or very high magnetic field and very, very high frequencies. And most of the quote unquote experts that do this kind of stuff today do these experiments in extremely strong magnetic fields. We're talking 20 Tesla, 30 Tesla, cryogenic, liquid nitrogen, liquid helium temperatures, and they're dealing with frequencies almost in the terahertz. I spoke to a guy who is in Ivan, who I hope to bring on at some point, who is working on a 673 gigahertz gun diode that will cost $500,000. So they're getting up there. They're almost at the terahertz with those frequencies. But in this setup, we're working at about a third of a Tesla for most of our experiments, which is why that corresponds to about 9 to 10 gigahertz, which, strangely enough, 9 to 10 gigahertz are set aside for space scientific exploration. So that's exactly what we're doing here. Here's a couple more iterations of the same thing. We're seeing more blips. They're moving all over. Later experiment, this is in the, this is a zoom in of some area that we thought there was a blip. So it's only going from 3100 to 4940 Gauss instead of the 2000. So this is a shorter experiment. This would probably have to be lined up somehow with those. Over here we see a very sharp dip. This is sort of interesting. So OBS was recording during this experiment. So all the information that you're seeing right now is recorded on the computer for some of these experiments. Some of the OBS files are quite large, in the tens of gigabytes. So this is definitely a blip that we'd want to look into, because this kind of thing is a sign that there might have been some resonance being found there. Okay. Then we moved over to a 1 gram sample, which is inside right now. And what I did differently with this sample was we made it half of a wavelength in length and a quarter wavelength in height. So it's basically a rectangle of super pure aluminum. I think it actually has 5 nines. Yeah, 5-9 aluminum. At least that's what's advertised on the box. And I just shaped it with a hammer. First one didn't come out so great. Second one came up pretty close, and then I sanded it for the final bit. And then in a later run, we ran it covered in ferrofluid because, according to Alzafon, covering the sample with iron, the aluminum with iron, should help increase the dynamic nuclear orientation in the sample. All of this has been uploaded to our WhatsApp group, and we have a team of data analysts led by Don Sadaya, who are actually looking at all this data and trying to make heads or tails of it. But really right now, I think we need to work more on getting rid of our noise floor, because I'm about to show you this. This was ran from the morning till the evening. So instead of 15,000 steps, it has like 103,000 steps. So something interesting must have been happening over here. This has probably got something to do with the air conditioner, the wind flow in the building. I don't think this was. I don't think this had related to any cars that were across the street or something like that. This is a control test. Nothing should have been happening during this test, except save for the first 15,000 points, and like maybe a fifth of the way in. That's where you'd expect to see something, because that's where a magnetic field was actually in play. But past this point, there was nothing. There was nothing going on other than the fans, the air conditioners, and the traffic. Nobody was in the building. So we need to get this as flat as possible before we can consider those other blips to be serious blips. Of course, the range over here is 0.99 to 0.975. So it's not that big of a range that we're looking at with differences in weight. We hope to see 0.20, 80% weight loss. in a future sample. So these are some of the troubles that we've been running, and I'm going to stop the screen share. So that is one thing that we've been concentrating on, is getting that noise floor down as much as possible. Probably have to put up a door or something to do with the airflow in the shop, and maybe run them at night as well. Another thing we have going on over here is way too many samples to run. We have piles and piles of samples, and people don't stop suggesting new samples for us to try. It's almost, yeah. I mean, in this box, this bin alone, I have like 30 samples in here, and these all need to be machined down. We've got various different powdered metals and powdered metal oxides in various forms mixed together inside of epoxy. I made this back in the day when Jeremiah was here. Me and Jarod were having a conversation the other day, and he found some book that suggested that bismuth can act as a dynamic nuclear orientation multiplier to the second harmonic or something like that. I wasn't really sure what that meant, but I was thinking maybe we should try a bismuth sample surrounded by aluminum and then surrounded by iron or something like that, and we can cook that over here inside of our vapor deposition machine over there in a clean room, and try that as a sample as well. The bismuth in the center would be great to have, because then we have a much larger, heavier sample to play around with. Another thing I've been thinking of doing is getting some sort of force dampening to hold the scale, because if the scale itself is sitting on top of the Faraday cage, which may be part of the problem. If it was inside of the Faraday cage, it would be affected by the RF, and we've seen this already. But when it's above the Faraday cage, it does not get affected. But the problem is the construction of the Faraday cage sort of amplifies these wobbles of energy. So we have to think of ways of mitigating those problems. We also have sample of osmium, which is extremely dense. Unfortunately, we probably won't be able to use that because the its dimensionality is not, it doesn't really work with the frequencies at hand. But that would have been great. That would have been a full like 32-gram sample that could fit inside that cage, inside the RF chamber. And I think I'm done over here. Actually, no, we have one more thing to show you. So the polarized aluminum, the ones that were actually done properly, we made some samples out of the parts that were most highly crystallized. And I don't know if I can get that in focus, but you can see the crystalline structures over there. That was created by cooling it extremely slowly through the inside of the magnetic field. It was done literally inside the magnet that you're seeing, the electromagnet that you're seeing to my side. This one is one wavelength by half, and by a quarter, and this is a half by a quarter. So both of these should resonate nicely with the 9.88 gigahertz that we have going on over there. So those are some future samples that we'll try and cover them with iron in a later run, and who knows what else. Maybe we'll cover them with bismuth too. And that's actually something that David Alzafon, if he's watching, he recommended we try aluminum, bismuth, aluminum in a tri-layer setup to amplify these effects. And with that, I'll hand it off.
Mark, thank you. Thank you. You know what? We owe Mark an applause. You have been on fire. Most folks don't know this. Mark and I talk all the time. You have been on fire like all month, just one thing after another, after another, after another, and with more to come soon. So, yeah. Well, so let me do this. We have, you know what? I want to go to Brian St. Clair next, because Brian is actually doing stuff too. So let me switch over to Brian, and I'll take Mark out for the time being. Brian, what do you have for us, sir?
Well, we've been working on the new Trammel machine. Like I said before, I don't want to show too much of the proprietary inner workings of it, but we do have a framework going back here. It's aluminum. It's much lighter weight. We're going to have some things that turn, things that spin, things that move. Ross, I know, was talking about the plates, the discs with an X cut in them. And I do have one that I can show. This is aluminum. It's 3/8 thick. This is actually not one that I'm going to be using, but I just kind of wanted to let everybody get a quick peek at it. Other than that, I mean, we're just plugging away at this. This one is gonna. It's promising to be well under 100 pounds total weight. I'm really shooting for a little less than that. Depends on what the motors end up weighing when we get done, and whether or not we use one motor, two motors. It's we're making some radical design changes to this. So you know, other than that, there's not an awful lot that's going on. I just I did want to show folks that, you know, we're still working at it, and hopefully soon we'll have some more testing that we can show live.
Oh, okay, I'll bring myself back in then. So Brian, again, big hand for Brian as well. Thank you for continuing to plug away at that. I know you and Ross have been working together. You guys are doing remarkable work. We have, so I think you're the only two folks that we have with us today. But, you know, and let me bring Mark back in, and I can bring Jarod in and Michael in as well. In terms of lab work, you know, there are so many people out there building things, but for some strange reason on a Saturday afternoon, it's difficult to get people to just show up. I'm not sure what the deal is with that.
How about we post the StreamYard link and get a comment?
Might have something to do with the sunshine.
Yeah.
That's it. Ryan,
yeah,
I
well,
love your headset, by the way. Very clear.
I think the sunshine definitely is a factor, and it looks like, let me see, Will's camera is still on. Guys, why don't we do kind of an open discussion, and we'll put the StreamYard link up there. I will put that into chat as soon as I can find it. There we go. Okay, and we would just ask people to kind of keep it clean and try and keep it focused, and yeah, but I'll put that up there. That's our StreamYard link, everybody.
So, Mark?
Yes, Michael.
So
yeah,
I
so
had a question.
this is open discussion.
You were showing the in the image below, the dark looks like a oscilloscope screen.
Spectrum
you were
analyzer.
showing it looked like, right, the spectrum analyzer, where it was like kind of like breaking down. It looked like a dielectric breakdown effect, where basically so I'm curious if
what was happening was the revert. So what you're looking at there is the reverse power coming back from the chamber. So we're pumping RF energy in, and then there's the SWR, the standing wave ratio, that's coming back. Now, what we're receiving back is changing, and as the SWR changes, that's how you get an EPR spectra. So when you see an EPR graph in one of these science books, what you're actually looking at is magnetic field sweep and RF frequency coming back. So that's how we know from those two parameters, you're able to tell what's going on inside the core of the atom. Are there free radicals or whatnot? And I think William could probably chime in on this as well. He seemed pretty knowledgeable about it. So the reverse power that was coming back was changing, and we think we nailed it down to an issue with the amplifier getting too much power bouncing back into it, because the power that you actually saw there is going through a very powerful what do you call it, resistor, an attenuator. It's a 50-watt attenuator before it hits the screen. So that's why it was only 3 dBm. But it really was probably positive 20, positive 30 or something like that. There was significant wattage coming back, but when it hits that attenuator, it bounces back and goes to the amplifier, which then heats up, and then we end up with this much broader spectrum, which is why I'm saying we're going to probably have to add one of these guys, these circulators, in to act as like a filter to remove that extra energy from hitting the amplifier. Keep it cool.
So you think it's an amplifier effect and it has nothing to do with the properties of the sample, like maybe the sample's getting warm or something?
Yeah. Well, we're pretty sure of that, because if I turned it on again right now, you'd see the nice the nice shape. Also, if I were to,
well, I mean, is the sample? Have you measured the temperature of the sample while it's being in RF field?
I don't know if you remember, but about 2 years ago or a year and a half ago, we had a different waveguide chamber. Right now, we're going with a round one, but back in the day, we had a way overmoded waveguide that was suggested by Tanya Seletsky. And it turns out that was completely inadequate. But in that chamber, I stuck all the gizmos possible. There was a temperature sensor. There was a spy camera, a whole bunch of stuff. We did see movement of the sample in that highly overmoded one as well, which was pretty cool. But
no temperature effects. So you think it's
there were temperature effects in that setup? Yes, there were.
There were temperature effects?
Yeah, but that was with powders, and I think we need to go back to powders in order to get this done right. With the metal samples, I have not seen any temperature rises yet, and that could be just because they're not getting that. Our issue is really with the sample, and we're not actually pumping the energy into the sample. It's actually just bouncing around it or something like that.
Well, what I was thinking, there could be eddy currents that are forming in the sample, and then it's building up over time. It looks like it's not instantaneous, but then you can see those little spikes show up, and then after it's basically saturates the amplifier, it looks like at some point. So if it's on the amplifier side, I would think you could filter that out, like you suggested, maybe with some capacitors, actually, some those little chip capacitors that are high voltage. How high is your voltage?
This is 9.8 gigahertz microwaves.
I know that's the frequency. I'm asking the voltage though.
I'm not really sure what the voltage is. You probably need vacuum capacitors.
So it's not.
Actually, like we have some vacuum capacitors. I wouldn't even know how would I attach a capacitor. Actually, we have variable vacuum capacitors. Tom, can you grab them?
There you go.
The closed room on top of the table. So
basically you tune the capacitor to the, and it'll cut out those spikes. Basically, it'll filter them out.
But where do we attach it to? This is going through. This is literally going through waveguide. I mean, this is how
going into the waveguide. Where's the power to the amplifier coming from?
That's coming from PSENG, the local power plant, 3-phase. I mean, it's getting fed through the RF is getting fed through a waveguide, which is literally this is called WR90.
Yeah, I'm not talking about the waveguide. I'm talking about the amplifier. No.
The amplifier puts out RF in a waveguide. It comes out as a waveguide.
Right. So is the amplifier kind of like a klystron for the waveguide?
No, but it's a traveling wave 2 amplifier. We do have klystrons here as well.
Okay,
no,
so
they're in a cardboard box.
Okay, well, there's just some ideas. It's either on the amp end, or it's on the, or it's on the. It seems like it has to be from the power supply, the power source to the thing, or it's got to be to the sensor. So
if you're trying to tune the circuit, I don't know how you'd add capacitance to
yeah, I would have to see the circuit. You're right.
I mean, this is what the circuit looks like. It's literally a tube. Here's a variable vacuum capacitor. So I didn't even know how in the world you'd attach this and what you'd attach it to.
Gotcha.
But we got one. I'd be pretty scared to be around this if it was resonating at 9.8 gigahertz. I put my hoodie all the way up. We have spare hoodies over here if anyone wants to come in for a visit while we're running stuff.
My son gave me for Father's Day. He gave me a pair of RF shielded briefs.
Oh yeah, I have them hanging over here too. Yeah, so we use that same material to make this, and a friend of mine's mom actually sewed it up, and we made a bunch of them. They're really great.
Yeah, well, I told him it was too late. I already been fixed.
Hey, Mark, I got a question for your experiment.
Yeah.
When you had it set up so the waveform got like spread out and rounded out, and then you turn it off, have you at any point noticed any spurious effects after removing power, like as it decays in energy once the energy is removed? If you get any spikes that come off of that broadened waveform when you turn it off, like it's, relaxing the spins or something?
What I think we're looking at there is the traveling wave tube is overheating, and it's, instead of putting out just the frequency we want, it starts putting out noise. That's what I think we're looking at. And Todd agreed with me. That's the theory we're going to go with for now. It happens every time we turn it on, no matter what the magnetic field strength is at. And if we shut it off for a little bit, it goes away. I can show you that right now. Turn it back on. And it's going to warm up, and then when I turn it on, you'll see the same thing happen. And it takes a couple of minutes for that effect to start. So yeah, that's what I think.
Have you been able to do sweeps on those tubes to be able to isolate to see if it's the tube itself heating up or if it's something with the material?
Yeah, because if it was the sample heating up, and we stopped the RF for a while, we'd see the same thing. I get your point. I don't know. Jarod, I think you're muted.
I was saying, or you could just remove the sample and do the test again and see if the overheating hump looks any different at all.
Oh yeah, that's an idea. I think we did that. Or did we? Yeah, I did that in the very beginning when I was testing just the chamber. So yeah, I already ran that experiment to isolate this problem. But again, these are baby steps towards building our inertial dampening. Hopefully that's what it is, an inertial dampening process. And these are the little nitty gritties that you have to deal with, on a daily basis. If anyone else wants to join in, we have a couple room, spots in the room.
Do you know if anybody makes like Peltier tape or something so that you can try to transfer the heat off of the pipe somewhere else, but not have to have like moving airflow for it?
I wouldn't put a Peltier device or anything that's removing heat from the pipe, because that will screw with our numbers even worse. Especially no fans can be in there. That's definite. That would just increase our noise problem.
Or for the waveguides, you could put some around the waveguides.
That's true, but I think most of the heat is actually coming right here. You can feel it. When you turn it on, you can feel the heat. The room actually gets warm from it. All the reverse heat that's coming off of there.
It might be the power supplies in the RF gen itself, the RF amp itself. That as those are, over cranking, overheating, those op amps and they're overheating, they get a little bit less precise in their resonance. So
the op amps. It's possible that it's that as well. Yeah, I hope so, because those are solid state too, right? Yeah, from what I've seen, they're the little 12 volt, and there's like 3 or 4 of them. I opened this up a couple times. There's like 3 or 4 of them in there, so it's giving a lot of stages. Okay, it's about ready. I'm gonna power it up and give you guys an idea what it looks like again. You'll see the same thing happen. And here we go.
You could try swapping out the heat sinks for those transistors in there, those op amps. That probably would help at least eliminate that possibility.
So the peak is at 1 dBm, and it should start falling apart in probably 3 minutes or so. And if I put my hand over here, I could, it's not warm yet, but it'll start getting warm when this happens.
Have you used your IR camera on the setup and seen if there's a particular spot on the waveguides or on the power supply that's getting hot?
Haven't done that yet with this particular setup. I have done that in the past, and I found that normally the isolator, which is essentially what I was trying to build over here with the circulator. The circulator is an isolator with a resistor on one side, or attenuator on one side. If that would get warm sometimes, that maybe there was an incident when it got too hot and it's fried now. I don't know, but no, it didn't start happening yet, but it'll happen at some point.
Good deal. Well, guys, do you have anything else? I mean, it doesn't look like we have anybody. Again, we threw the link out there. It doesn't look like we have anybody else.
Tim, do you want to go into the news?
Well, you know what I can do? Yeah. So I guess what I probably should do is showcase our media partners for you. Let me do that. And I don't have any of the media partners with us. So I think maybe what if we just do kind of a brief wrap up? What I will do is walk people through the website real quick, though. Okay.
Oh, what happens if we get 0 results? Then we change something and try again. We've got lots of 0 results. Very good at getting 0 results.
Okay, so this is the APEC website, and I'm sure you guys have all seen it. Yep, and okay, it's presenting. So again, I just want to showcase this to everybody. Let me go to, first of all, Research Labs, our lab partners. You can learn more about the lab partners that we've done a lot with right here on the top of the page, right? As well as my growing list of just folks that are doing actual work. And if you know of any others, send them over to me. Let me know, and I will add them to our list. A few of these fellows, unfortunately, have left us, right? Like Paul Murad and Paul LaViolette. But, we're trying to make that more comprehensive. So the media partners, I want to show that to you now very briefly. Again, you guys saw this in the last conference. I'm going to show this to you again. They are helping us to promote APEC. They are helping us to get the word out. Yeah, the EM drive isn't dead yet, says the guy who invented the EM drive. Popular Mechanics did an article on APEC. This goes way back when. Roger Scheuer actually came on and talked about the EM drive. Go down to our key promotional partners. So Alien Scientist, we have Jeremy Riss with us today. And in a moment, if he wants to, I can give kind of I'll give him a few minutes to kind of run through his latest stories. So Bernie Conkin, Crypto Alchemist. Bernie is not able to join us, but Bernie is doing podcasts on his channel. He is doing stuff typically every week, sometimes 2 or 3 per week. So definitely visit our media partners page and check him out. Professor Simon Holland, he has a massive subscriber base. He is doing a ton on the UAP phenomena. Then let me see, Generation Z with Dave Rossi. Right. And Dave is a past APEC presenter. He has been on the conference and presented about it. I believe he was talking about the PACE device and some others as well. Definitely take a look there. And of course, Tesla Tech, our longtime friends with that Albuquerque, New Mexico conference. So Steve Ellswick came on last session. Steve has his own channel. The important thing to know about Tesla Tech is they are doing updates. He is uploading his video library. He's got hundreds, if not thousands, of conference presentations that are going up online. And then, of course, there's my channel as well, Tim Ventura Interviews, and I'm continuing to do interviews there as well. I've been digging into the UAP phenomena a little bit more. So, you know, this summer, we're going to see a lot more on that. I'll just scroll down really quickly. Again, futurism.com did an article on APEC. NASA, DARPA, MIT scientists met to discuss anti-gravity tech. And that is not an exaggeration. We have had scientists here from some of the most prestigious institutions in the world. And it's an honor to have them. It is an honor to have them. And it's honestly, it's an honor to have everyone who presents at APEC. So that is that. I am not going to show you our next APEC quite yet, but it will be up on our website probably tomorrow. We are planning them out in advance. Visit altpropulsion.com. Please register for our update list. That way you will get a notification when we start to live stream. And we have amazing stuff coming, amazing stuff. And, you know, I mean, as a moderator, I'm kind of a witness to this as well. Amazing stuff is happening here as well. The stuff that is being constructed and tested and built is absolutely tremendous, right? And as you can see, it's on your screen right now. So I think that is what I have. And we are at the top of the hour. Guys, should we close things down for today?
Wait, I just wanted to show them the that hump that's being created. So it's getting pretty warm right now, and we went from positive 1 dBm, that's going through an attenuator, of course, to negative 1, negative 2, something like that dBm at the peak, and soon it will start popping up those spikes as it warms up, and we'll see that same effect happen again. I don't know, maybe it is related to the sample. I don't know.
Yeah. Well, Mark, it again, amazing. Absolutely amazing. And I mean that. I'm not brown nosing. I mean that.
Thank you, Tim.
I also brown nose.
Yeah, we can keep everyone in for now until this actually happens, because otherwise we're just scared, waiting for grass to grow. But that's kind of what science looks like. A lot of the times. Hopefully let the grass grow overnight, get it, be able to run several experiments over the course of the night, keep the noise to a minimum, put up the doors, and get better samples, and hopefully we'll end up seeing something.
Wonderful. Wonderful.
While we're waiting for that, is it all right if Jeremy plugs his alien scientist stuff, especially with his awesome interview with Targ and Sarfati yesterday?
Yeah, Jeremy, go for it. Tell us all about it.
Yeah, I should have. I seen a whole bunch of good stuff, of course, today. Research started popping up about Russell Targ and Sarfati today. So I got a whole bunch more questions to ask those two. So I got to get them on again. But yeah, it was an exciting little podcast. I threw it together kind of last minute and invited them, and they jumped on. I guess Jack forwarded the email to Russell. I didn't even know his email, but Russell and him jumped on, which is awesome, getting the old timers on there to share some of their knowledge about the whole history of a lot of this stuff. So yeah, that was really cool. You guys can go watch that. I got to have Jack go over a bunch of different stuff that people have been looking at. Like we went deep into the Eric Davis warp drive models, which, you know, were I don't know, they have the official stamp of the U.S. Air Force because apparently, you know, they hire scientists to do some of these studies. And that was the author, the title of the thing is Teleportation Physics Study, which was, I thought, interesting, at least. But so anyways, Jack went over it and kind of dismantled it and showed us in the equation on doing and a lot of the math and stuff. So helped kind of clear some of the things up, at least for the engineering people and who are paying attention to all this. I think these conferences are really waking a lot of people up. It's really getting a lot of people to think seriously about these topics and to dive into the physics and think differently about, you know, things they think they understand, or, you know, the smartest people in the room who are always correcting everyone. And you know, we welcome those kind of people all the time, because it's a community of those types of people constantly correcting each other, or asking, you know, difficult questions that will, you know, put our understandings and beliefs to, you know, push them to the edge, so to speak. So yeah, that was it's not showing in the video list. I'll have to make sure it I have it up on my channel. I'll go and change that right now.
And you know, while he's doing that, actually, let me, if it's Mark, if it's okay, let me jump in really quick. I want to show
Tim. It's actually happening right now. This is only going to happen for a couple seconds. So right now is when the spike is going from being a spike to being an entire mountain. And this is what I was referring to. It is pretty hot over here, so I think it does relate to that. But who knows? Maybe
the amplitude increased too. The amplitude increased.
Oh no, that's decreasing. It's -2. It's in the negative range. Before it was like, it started off +1, then it went to -1.2 right when I finished talking.
Gotcha.
And now it's at -2. It's been steadily dropping, and basically the sharpness of the signal is collapsing.
So the signal to noise ratio is going way down.
Yes. The RF signal noise ratio. And I'm going to put it in standby for a little bit. Tim, you can do your spiel, and we'll turn it back on, and you'll see it has time to cool off.
Oh, sorry about that. Okay, sorry about that. Wrong button. Well, yeah, Mark, actually, let me share really quick. I forgot to share this earlier. I do want to share this, though. This is important. So the APEC schedule, you can find this. This is on the altpropulsion.com website. Just the events button, go down to schedule and format. And what we have done is, so this is a tool that we use called add event. This is in here. So you can see it takes a moment to load. We've got the schedule for these loaded way in advance. So I just want to show you kind of two things about it. So the first one is when we have stuff planned out, for instance, August 5th, right? I already know what's coming up there. We've got that planned. Dr. Raymond Chow will discuss spin gravity, Tammy Padina on experimental propulsion, Kevin Newth on updates. So that is in there. Also, we have placeholders because we know, even if we don't have it planned, we know when these will be for both of these, the open mic and the webinars. And as you can see, this goes out to pretty much infinity. Then if you scroll down a little bit more, you can see it in a little bit more user-friendly format. So if you want to know what's coming up on APEC, this page is the one to use, and it has different ways of doing it. It's in the schedule and format. And again, if you want reminders, and I would urge you to do this, join the APEC community. It's the join APEC button. We don't share your info. It's all private. We don't sell it. Nothing weird, anything like that. We will just send you, basically, it's 2 updates per event, one a couple of days before and one the day of. So that is all I had there.
Awesome. Thank you, Tim. Thank you, Jarod, for that excellent TR3B presentation. Mark, as always, interesting updates, and keep plugging along with the great research. I feel like even if, you know, some of these things are negatives, negative results, it's we can cross it off the list and move on. And,
right.
With
this experiment, though, there's a lot of variables to play with. So we're going to cross off the specific thing we did and then change something small and move on with that. That's kind of what I've been looking at. Also, because this experiment, the equipment setup to get this far is daunting. We're talking about equipment here that cost as much as a house when it was first produced. So, not even to mention that even a billionaire with all the money in the world right now would not be able to buy this type of equipment just simply because it doesn't exist anymore. Although, given enough time, of course, anyone can get it. Oh, Richard Van Derek just joined. That's going to be
awesome.
Cool.
Well, keep your Teflon or your steel underwear on in the meantime.
One second, I'm about to turn this back on, and nope, it's still a mountain. Whatever's happening did not get reversed yet.
Mark, you haven't left it on like that for a long time, have you? Like let it stay as a hump for like an hour or something?
Yeah, we got Richard here.
For hours at a time, yes.
Richard, any updates from your lab?
Let's get everyone on here. Yeah.
Oh, sorry about that. No, not really. Not what I'm really prepared to talk about. We're doing a lot of work for NSF and then the Air Force. So, our NSF project was to generate metamaterials that generate a longitudinal force that you could use for propulsion. So we're just kind of working on that. We're getting these materials made. We might be working with some papers on gravity modification, but I really don't have any other updates except we're just kind of plugging along.
Richard, I like your profile picture over there. It looks like some of the lightweight, high voltage power supplies that me and Jeremiah made when he was down here. It actually looks like you're using the exact same tubes that we have over here in our HV box.
Oh yeah, those high voltage tubes. Yeah, so that was those rotating current elements. So you charge them up and rotate them and try to see how much force you get. Yeah, but those things are too hard to eliminate all these other effects, right? Because you got that rotational inertia you got to compensate for and the rest of that. So that just kind of muddles all your data. That's why kind of like we kind of
really strong. Don't mute yourself, Richard. Another thing I wanted to say was when we ran your experiment, we saw a very strong attraction to Earth's magnetic field. Very strong, stronger than you'd expect from a regular compass. And this is something that Richard Eskridge actually discovered as well. He wrote a paper on it while working for NASA, that rotating magnetic fields, depending which way they're rotating or which way the magnetic fields are oriented, can push and pull against Earth's magnetic field or in the direction of rotation of Earth. So you're pointing it at the North Star, and you actually get very interesting results. So you may want to fly down to Ecuador. Tom's actually going there next month. You may want to go down to Ecuador because at that point you're set up at 90 degrees to the poles, and anything that's horizontal is pointing at the poles. And you can actually eliminate that as a contributor, or turn it 90 degrees, you'll measure it as a contributor.
Okay, yeah, but the magnetic field is mainly from that motor, right? Because the rotating charged disk, they don't really generate a magnetic field if you can hold the charge stationary to the disk, right? If you can get the charge to rotate at the same speed the disk is, by putting some type of cut in the disk, you shouldn't get any magnetic field from it. So the magnetic field you'd be interacting with would be the one from the motor.
Well, what do you get when you move an electric field through space? Don't you get a magnetic field?
No. So you get how a magnetic force in a wire works, right? The electrons are moving through the wire, and because of Lorentz contraction, the charge density increases. So that's really an electric effect, right? And then, but because it's in a material like a conductor, you generate a magnetic force because the stationary positive ions in the conductor are stationary and the electric current's moving at a velocity. So you take the two force vectors and then you basically sum them up and then you get a magnetic force. So if you just have a charged object, let's say take an electron beam. So an electron beam doesn't generate a magnetic field, but it will be bent by a magnetic field, right? Because the ion or the charged electrons, as they move through the air, don't have another material to interact with, right? So that seems to be one of the things that a lot of people just assume, that any moving charge generates a magnetic field where it doesn't. The charge has to be in a medium of some kind. So it's isolated like a rotating charge disk in the air, or just the ions moving through a magnetic or moving through a vacuum. Yeah, none of those things generate a magnetic field.
Have you
They don't
tried
generate
that?
magnetic.
Because that's an experiment I really wanted to try. Is like basically a disc or a ribbon, similar to a Van de Graaff machine, but you have it round and build up a charge on it and spin the entire charged Teflon or plastic device in a circle. And we're looking for like a shielding effect, similar to what happened at the 3M plant back in '95. Are you familiar with that event?
Yep. So why don't you use a charged ring? That's what we used. You take basically a disc, and you can charge that, put a ring around the outside of it, and then you're able to get a pretty good charge in that ring. And then so you can use a conductor there, but then you have to put a cut in the ring so it can't circulate in the ring, right? So now the charge is going to be stuck on the ring. So then you have to you basically have to cover it over so the charge doesn't leak off. And then the next thing to do to make sure the charge is on there is use one of your tubes to say put a positive charge on there. So that way you're really just measuring the charge increase from the rotating ions, right? Because it doesn't have to be electrons. If you use just the ions by pulling some of the charge off the ring, you know that the ions aren't going to move separate from the physical structure. So then you try to measure the magnetic field from that. If you put an electric field meter around the outside of that and you let that run long enough, you're going to notice the potential on the ring starts to increase. And that's an experiment to do too.
Okay. Have you been able to remove the electric motor from the apparatus to rule that out?
No,
How about
that's
rubber
one of the
bands?
problems. So,
How about rubber bands?
well, so you have to use so when you use a big disc, right, you get a lot of momentum on it. So you can use a very small motor to spin it, right? So that's one way to try to minimize the effects, right? So I don't know. I mean, there's electrostatic motors out there, right? I mean, there's a possibility there.
In another device, the kinesmatic effect generator, they used airflow in order to remove any magnetic fields. And they were basically just trying to prove that rotating masses create some sort of electric field. And in order to do that, they had to remove all the magnetic components. They used airflow. Basically, you'd get like an air gun or something like that, get it up to speed, somehow balance it out quickly enough in order to get a decent reading.
Well, okay. So the other thing you have to watch out for too. So an electric current inside a conductor is moving at millimeters per second, right? So if you have 1 amp moving through a conductor, you're going to end up with a magnetic field of some value, depending on how far away you're measuring it. So, but when you start rotating things, now those charges are moving at much greater speed. So if you're using a rotating object, you could get those running at, say, maybe 100 meters per second, right? So now the magnetic fields meters are not going to read that correctly. These are all calibrated to a conductor, right?
Right.
Yeah. So you have to start using other different ways to measure them too. So, what are you thinking of trying that experiment on one of these? Do you want to just charge something up and
I mean, I have a whole box full of we call it the rotating magnet experiment, but it's very similar. It's right next to the Van Dijk experiment because it uses a lot of the same hardware. But,
yeah. So when you call it the rotating magnet, what do you mean by that? You mean you actually rotate a magnetic material?
Can you go with the box, please, Tom? Also, yeah, it's just an array of rotating magnets. That's what it is. In various configurations, and when you point it at North Star, it creates real thrust. I actually ran it on a live stream with Jeremy Reese right after the SETI conference, and it was inside of a Faraday cage, pointing at the North Star, and it generated a couple grams of thrust before I burnt out the motor. So this is rotating magnetic fields.
Yeah. So you think that's doing that? You think it's doing that because it's interrelated or interacting with the Earth's magnetic field?
Rotating magnets. think it's in F3 or something like that on the left. It's based off of Richard Eskridge's paper. I think I have it right here. 1 second. Oh, stupid now. Oh, yeah, here. Study of the Pope-Osborn angular momentum tensity theory. You remember when Amy Eskridge kicked me off of that other conference, claiming that I was violating an NDA? It was over this paper. Estes Park, yeah.
Yeah, you know, I've read that paper once. It's been a long time ago. So what was his results from that paper?
Same as ours. It works.
Yeah.
So these are this is magnetic fields. They're alternating. You can see from the black and the silver part. And we stick this on motor arrays, or yeah, we got some different RC motors on a plaque, and point it in that direction, hold it in place, and watch it lose weight or gain weight. Depends which way you have the magnetic fields and how you spin it.
Yeah, but then you have to eliminate, is it interacting with something else in the environment, right?
Well, the only thing it could be, what it could be interacting with is probably Earth's magnetic field, but that's only half of a Gauss. So that doesn't make sense for the amount of thrust that we saw, unless there's some sort of another form of magnetism that we're not aware of. Just like you said, there's another form of electricity that regular meters can't read. This is maybe another form of electricity, of magnetism, where it's rotating.
Yeah. So on my stuff there, I can't eliminate it was interactions between the magnetic part of the motor and stuff. So yeah, I never really tried to resolve any further on that. You know, I remember seeing your experiment there, but you know, that's the problem with trying to use rotating objects. You know, how can you verify this not interacting with something in the environment to prove that it's actually working, right?
Right. And this setup, we had it on a 3-string pendulum. So there was a string coming in from this side, a string coming in from this side, and then finally a string holding it from a center point that had the actual gauge measurement, the weight measurement on it. And this was all inside of a Faraday cage, in the center of our Faraday cage, actually. And I powered it on remotely. So it had a battery hanging attached to it. And it's controlled via like a remote control controller, and just slowly sped it up and watch the weight loss. Or I think it was weight gain in that scenario. It actually gained a little weight. But again, the entire thing was shaking. The amount of inertia stored in this device is much greater than the weight loss you're seeing. So there is a noise floor issue, you know, if everything's not perfectly balanced.
Yeah, you know, and I agree. That's the problem I had with rotating objects is, you know, I could never resolve what the force is being created from, right? Because, you know, sometimes you get good results and sometimes you wouldn't. So, yeah, I was never able to resolve whether it's not some of these other effects.
Well, one thing we did see that was very cool when running your experiment was it was reacting very strongly to Earth's magnetic field, and we knew that because it would reach a certain point and then slow down, and then, you know, barely make it around. Then it would speed up, and then right there it would slow down. Right past this point, when it was facing Earth's magnetic field, it would slow down, which is why I'm recommending you go down to Ecuador, because over there it's perfectly perpendicular with the ground. And you'll be able to get a really strong interaction with just a pendulum.
Yeah, but the other idea here is, you know, the Earth's magnetic field is so weak. You know, could it really have that much interaction with it? Right?
It's a lot stronger than you see on a compass. A lot stronger than that. And which is what this paper dives into.
Yeah. Okay. I mean, so you're actually working on things that I'm not anymore.
Here's some of that's Richard's work. Yeah, they were using looks like Tinker Toys in order to get it oriented with Earth's magnetic field. Oh, and they put this around it for, I guess that was for airflow, and the entire thing went on a scale. Like a foam base with plastic surrounding it to stop the airflow. Yeah.
All right.
Richard?
Well, I mean, how's your experiment going there? I mean, have you actually measured that much from it?
So the best results we've ever got with this experiment was with a different configuration where we had the electromagnet, instead of pointing horizontally to Earth, it was perpendicular to Earth. It was pointing horizontally to Earth, and I used a thin piece of aluminum covered in ferrofluid, and we saw like 18% weight loss. Recently, we've been trying to up that number by trying different configurations, and right now we're seeing lots of noise. We perfected our data research system, and I went into that earlier, showing everyone the graphs, which is basically showing you weight over time. What we're trying to perfect right now is the sample material, and I actually got in contact with some guys from MUFON and from Roswell who are going to give me some samples that they think came from a flying saucer. Great thing about this thing is if you can get a sample that's small enough and fit it in there, we can run it. And EPR, electron paramagnetic resonance, anything that has that has valence electrons will have some form of an EPR spectra. And if it has an EPR spectra, let's try to see if it can, lose weight while it's going through those nuclear orientation changes. We're basically trying to make coherent matter. Trying to make matter, core of the atom spins oriented in one direction. And hopefully that makes it easier to do 90 returns at 10,000 miles an hour.
Yeah, that sounds cool. It sounds like it takes a lot of power, though, right?
Maybe. I don't know. The amplifier behind me is a couple hundred watts. That's what we have to play with. So we're trying pretty small experiments. Once we got this figured out, we have an RF amplifier over there that can put out like 6 or 7 kilowatts at the X band, and that should be good enough for a small size craft using the same method.
Yeah, it sounds interesting. Good luck on that.
Thank you. Thank you. Are you still working for DARPA?
No. So with DARPA, that COVID kind of screwed up my ability to get things tested. So the only way I could continue with them is a no-cost extension. So no, I moved on to the National Science Foundation. So we're doing a National Science Foundation project with them. That's what I was explaining. So National Science Foundation is funding us to make these metamaterials that generate a longitudinal force in them when you run an electric current through them.
Interesting. What frequencies can you run those longitudinal waves?
Oh, yeah. So, we're just working with like 5 to 10 kilohertz, keeping it low.
Okay. And how thick is the sample? How big are they?
Oh, they're about 10 centimeters.
Oh, 10 centimeters. Well, if you have anything that you think would produce an effect with dynamic nuclear orientation, you could send it over here. We're looking for samples that are a bit smaller than that. I think the full wavelength is 31 millimeters. And so we'd want here, I can actually show you. So at 9.8 gigahertz, this is our sample sizes. And in order for it to resonate properly, it needs to be either full wavelength by a quarter or a half wavelength by a quarter, and various variations of such.
Yeah. So the stuff we're making is not really to be high frequency, right? We're really looking for the electric currents to flow at a very fast rate, like it maybe 1,000 meters to 5,000 meters per second, right? So, and then the dielectric material in there has a high dielectric constant. So high frequency is not going to go through them very well, right? They'll probably look like they're really high impedance to it. So yeah, we're working on different stuff. That's pretty much what it comes down to it, because the longitudinal forces we have would appear in the ends of the sample, right?
Okay. Yeah. So I guess you're using some sort of carbon graphite.
Yeah. Graphene-based stuff.
Graphene-based stuff. Okay, cool. We have a vapor deposition machine with the graphene setup too. You could layer graphene on top of Teflon or whatever.
Oh yeah. So how many layers can you make?
Every time you turn it on, you make another layer. Or you deposit more. It's not that sophisticated.
Yeah, I was going to say the other key is to get a uniform. Yeah, because to buy a sheet of say 5 layer, you're paying hundreds of dollars.
Yeah, I could make you 5,000 layers pretty easily. It also it spins around on a bed too when you're making it.
Oh yeah, but he's got to make him uniform. Well, that's cool. That sounds good. But yeah, so I figured I'd come out here and see how you guys were doing, and it doesn't look like there's too many people that showed up.
Actually, there's 122 people watching on YouTube. So what we're doing now with APEC is instead of having a Zoom call with 70 or 80 people that are not all very knowledgeable about the science, we're trying to send out the StreamYard link to the most important people that actually ask relevant questions and have subject matter experts, so to say. And everyone else is watching on YouTube, and they are commenting as well in the live stream. We're able to add that in. So this is a different software system. This is called StreamYard.
Yeah, I know. I logged in. I've never used this before, but it seems like a good app. Well, yeah, I myself got to go. I was just trying to check in and see what you guys are doing. I actually have to get back to the lab.
Okay, great. Thank you very much for showing up.
All right.
Please show up next time, okay?
Yep. Okay. Yep.
Richard,
Awesome.
thank you so much.
Richard. I got to get going here too, guys. So I'm gonna shut it down at least on Alien Scientist.
I think it may be that time then. So I think today's conference went pretty well. I did update our presenter stuff with PowerPoint limits and video notes. So that should be a little bit helpful for next time. And again, we have August 5th is already planned. I'm halfway through scheduling folks for September. And then we have open mics coming up too. And that's all on the Alt Propulsion site. If you guys hit that scheduling page, that's all there. You can add that to your calendar, or you can subscribe to just, 1 or 2 events if you just want to see those. I'm really excited. One of the things I've been saying for the last couple of weeks is there's momentum happening, and that's amazing.
Yeah, the open mics are a great chance for anons to jump on and share whatever. So if you're looking for that kind of a place where you say you have information but you can't feel anything, you want a spot to do it, and you need a microphone in order to talk and get some stuff out. That's the spot.
Okay, and we have Bernie coming on at the very end here. Let's see, Bernie,
Hello,
we're just wrapping things up.
Life off at work. I was trying to rush home in time to make it, but not quite. So I guess I'll have to present next week or next month.
Yeah, no, absolutely. Okay, well, Bernie, thank you. Have a wonderful drive home, a safe drive home.
Thank you. You guys too. Have a wonderful day.
Okay.
Later. Awesome end to the stream. The random Bernie.
Okay. Well, I'm going to end the broadcast then. Guys, a wonderful APEC. Thank you so much. Thank you to everybody watching and listening. I think today was absolutely awesome.
All right.
Thanks, Tim. Thanks, guys.
Thanks, Tim.